Imagine an advanced spacecraft, equipped with the best technology humanity can create, being sent on a mission to explore Jupiter up close. Engineers designed this spacecraft with super strong materials, extreme heat protection systems, and computers capable of withstanding almost any condition. The mission is simple: descend through Jupiter's atmosphere, collect data, and discover what really exists beneath those colourful clouds we see from far away. The spacecraft enters the upper atmosphere, where the sky is dark and the temperature is over 100 degrees below zero. Everything seems to be working perfectly. But then, as the spacecraft begins to descend, something terrible starts to happen. Winds hit the spacecraft with unbelievable force, over 1,600 kilometers per hour, faster than any hurricane on Earth. The structure begins to shake violently. Sensors begin detecting that the pressure outside is increasing rapidly. With every kilometer the spacecraft descends, the pressure doubles, then triples, then becomes millions of times stronger than sea level pressure on Earth. The temperature also begins to rise, from freezing to hot, then to very hot, then to thousands of degrees. The metal forming the spacecraft's hull begins to soften, then glows red, then orange, then white. The spacecraft is literally melting while still falling. Electronic systems begin to fail because of the intense radiation. Cameras stop working. Engines no longer respond. The spacecraft continues sinking through increasingly dense layers of gases that transform into liquids under impossible pressure. There is no bottom, no solid surface to land on, just pressure and heat increasing until the spacecraft is completely crushed and vaporized, becoming just atoms mixed into Jupiter's infinite atmosphere. Get ready to sleep while listening to this video and follow this impossible journey, discovering exactly what would happen to a spacecraft attempting the unthinkable, exploring the most hostile planet in the solar system from the inside out. Why could no technology we have today survive this descent? And what does this teach us about the limits of space exploration? Subscribe to the channel. Leave your like and comment what part of the world you are watching from. Get comfortable and relax. Let's begin. Have you ever wondered what makes Jupiter so fundamentally different from our home planet? Jupiter stands as a colossal testament to the diversity of planetary environments in our solar system. With an atmosphere so extreme, it defies our earthly understanding of what a planet should be like. Jupiter's atmosphere represents one of the most hostile environments imaginable. This gas giant, the largest planet in our solar system, possesses an atmosphere primarily composed of hydrogen and helium, about 89% and 10% respectively, with trace amounts of other compounds like methane, ammonia, and water vapor. But it's not just the composition that makes Jupiter's atmosphere so extraordinary. It's the sheer scale and the extreme conditions present throughout its many layers. The outermost layer of Jupiter's atmosphere, what we see when we look at the planet through telescopes, is merely the visible cloud tops. These clouds, composed primarily of ammonia crystals, create the distinctive bands of varying colours that encircle the planet. The visible atmosphere extends about 50 kilometers in depth, but this represents just the beginning of Jupiter's atmospheric mysteries. Beneath these clouds, Jupiter's atmosphere extends thousands of kilometers downward, transitioning through various layers with increasingly extreme conditions. Unlike Earth's atmosphere, which has a clearly defined boundary with our planet's surface, Jupiter's atmosphere gradually becomes denser and hotter the deeper you go. Scientists divide this atmospheric structure into distinct regions: the troposphere, the stratosphere, the thermosphere, and the exosphere. The troposphere is the lowest and densest part of Jupiter's atmosphere. Here, the temperature decreases with increasing altitude, similar to Earth's troposphere. However, the pressure in this region ranges from 1 bar at the top, equivalent to Earth's sea level pressure, to about 20 bars at its bottom. For comparison, The pressure experienced by a submarine at 200 meters below Earth's ocean surface is approximately 20 bars. As we descend deeper, the stratosphere begins, where temperatures start to increase with altitude due to absorption of solar radiation. Beyond that lies the thermosphere, where temperatures can reach several hundred degrees Celsius. And finally, the exosphere, which gradually transitions into the surrounding space. What makes Jupiter's atmosphere particularly extreme is what happens below these conventional atmospheric layers. As we continue our hypothetical journey downward, the pressure and temperature rise dramatically. At depths of around 3,000 kilometers, the pressure reaches millions of times Earth's surface pressure, and temperatures soar to thousands of degrees. Under these extraordinary conditions, hydrogen undergoes a fascinating transformation. The immense pressure forces hydrogen molecules so close together that they begin to behave like a liquid metal rather than a gas. This metallic hydrogen layer is believed to extend tens of thousands of kilometers in depth and plays a crucial role in generating Jupiter's powerful magnetic field, the strongest in the solar system. The winds in Jupiter's atmosphere add another layer of extremity. The planet's rapid rotation, completing a full turn in just under 10 hours despite its enormous size, creates powerful jet streams and winds that can reach speeds of 400 kilometers per hour. These winds flow in opposite directions in adjacent bands, creating the distinctive striped appearance we observe from Earth. The Great Red Spot, a massive storm system larger than Earth, has been raging in Jupiter's atmosphere for at least 400 years. With winds that can reach speeds of 600 kilometers per hour. Temperature variations in Jupiter's atmosphere are equally extreme. At the cloud tops, temperatures hover around negative 145 degrees Celsius. But as we descend, temperatures rise dramatically. At the boundary where hydrogen begins to transition to its metallic state, temperatures reach several thousand degrees Celsius. And at Jupiter's core, temperatures are estimated to be around 24,000 degrees Celsius, hotter than the surface of the Sun. The pressure gradient in Jupiter's atmosphere is perhaps its most hostile feature. From 1 bar at the visible cloud tops, the pressure increases exponentially with depth. At just 1,000 kilometers below the clouds, pressures reach hundreds of thousands of bars. By the time we approach the transition to metallic hydrogen, pressures soar to millions of bars. These pressures are so immense that they fundamentally alter the behavior of matter itself. Another aspect that makes Jupiter's atmosphere so extreme is its sheer mass. Jupiter's atmosphere doesn't represent a thin envelope around a solid body as Earth's does. It essentially is the planet. While Jupiter likely has a solid core, it's relatively small compared to the planet's overall size. The atmospheric and liquid layers constitute the vast majority of Jupiter's mass, making it fundamentally different from terrestrial planets like Earth. The energy dynamics within Jupiter's atmosphere are also extraordinary. Unlike Earth, which receives most of its energy from the Sun, Jupiter generates significant heat internally. In fact, Jupiter emits almost twice as much energy as it receives from the Sun. This internal heat source drives powerful convection currents that contribute to the planet's complex weather patterns and help maintain its extreme temperature gradient. This combination of immense pressure, extreme temperatures, powerful winds, and exotic states of matter makes Jupiter's atmosphere one of the most hostile environments in our solar system. Any spacecraft attempting to penetrate beyond the outermost layers would face conditions that no human-made technology could currently withstand. The progressive crushing pressure, scorching heat, and increasingly exotic physical states of the atmosphere itself would destroy even our most advanced materials long before reaching anything resembling a surface. The question of Jupiter's non-existent surface when we think about planets. Our Earth-centric perspective often leads us to imagine a solid surface, ground beneath our feet, perhaps covered by oceans, but ultimately a definitive boundary where the atmosphere ends and the planet itself begins. Jupiter challenges this fundamental concept in a way that's difficult for us to visualize. It simply has no surface in the conventional sense. Jupiter belongs to a category of planets called gas giants, and this classification hints at its fundamental nature. Unlike terrestrial planets like Earth, Mars, or Venus, gas giants don't have a clearly defined solid surface. Instead, they consist primarily of hydrogen and helium that gradually become denser toward the center of the planet. If you were to attempt a journey toward Jupiter's center, you would experience a continuous transition from thin gas to increasingly dense gas, then to liquid, and eventually to exotic states of matter under extreme pressure. But you would never encounter a moment where you could definitively say, "Now I've reached the surface." This reality creates conceptual challenges both for scientific study and for our human tendency to categorize and define planetary features. When scientists discuss Jupiter's surface, they're typically referring to an arbitrary reference point where the atmospheric pressure equals 1 bar, approximately the same as Earth's average sea level pressure. This reference point serves as a convenient baseline for measurements and discussions, but it doesn't represent any physical boundary or actual surface. It's merely a pressure level within the continuous gaseous structure of the planet. The absence of a surface raises fascinating questions about how we define a planet's basic characteristics. On Earth, we can easily measure a planet's radius by determining the distance from its center to its surface. For Jupiter, scientists must specify which surface they're referring to, the visible cloud tops, the 1 bar pressure level, the boundary where hydrogen transitions to a metallic state. Each choice yields different measurements and reflects the inherent ambiguity in defining the dimensions of a gas giant. As we descend into Jupiter's atmosphere, the gas becomes progressively denser due to the enormous pressure created by the planet's gravity acting on the gas above. At approximately 1,000 kilometers below the cloud tops, the atmospheric pressure reaches thousands of times Earth's surface pressure, compressing the gas to a density closer to that of a liquid than a gas, though the transition is gradual rather than abrupt. Deeper still, at roughly 20,000 kilometers below the 1 bar level, hydrogen gas is compressed so intensely that it transforms into a state called metallic hydrogen. In this exotic form of matter, hydrogen atoms are packed so tightly that their electrons can move freely, creating a substance that conducts electricity like a metal while maintaining fluid-like properties. This metallic hydrogen layer extends for tens of thousands of kilometers and is believed to be responsible for generating Jupiter's powerful magnetic field. At Jupiter's core, most scientists believe there exists a solid or semi-solid center, composed primarily of heavy elements like iron and silicate materials. This core likely has a radius of about 15,000 kilometers, roughly comparable to the size of Earth. However, even this core boundary represents a gradual transition rather than a sharp demarcation between different layers. The conceptual challenge of Jupiter's lack of surface affects our approach to planetary exploration. When spacecraft are sent to terrestrial planets or moons, mission planners can design landing systems with a solid surface in mind. For Jupiter, any mission must contend with the reality that a probe will never land. It will simply continue descending until it's eventually crushed by pressure or melted by heat. This reality was demonstrated by NASA's Galileo mission, which sent a probe into Jupiter's atmosphere in December 1995. The probe survived for approximately 58 minutes as it descended through the outermost layers of Jupiter's atmosphere, reaching a depth of about 150 kilometers below the cloud tops before being destroyed by the extreme conditions. At no point did it encounter anything resembling a surface. It simply transmitted data about increasingly dense atmospheric layers until it could no longer function. The question of Jupiter's surface also influences how we think about habitability and the potential for life. Our terrestrial concept of habitable environments typically involves solid ground, liquid water, and an atmosphere. Jupiter challenges this paradigm by presenting an environment that is entirely atmospheric, with pressure and temperature conditions that change continuously with depth. Some scientists have speculated about potential habitable niches within Jupiter's atmosphere, where pressure and temperature might allow for liquid water droplets to exist within certain cloud layers. However, these regions would be floating environments rather than surface-based ones, requiring us to reimagine what a planetary habitat might look like. Jupiter's lack of a definitive surface also affects how we understand its weather patterns. The planet's famous bands of clouds and storms, including the Great Red Spot, exist within the atmosphere rather than occurring above a surface. These weather systems can persist for decades or even centuries precisely because there is no solid surface to create friction and dissipate their energy. The deep interior of Jupiter presents other puzzles related to its lack of surface. Recent data from NASA's Juno mission suggests that Jupiter's core might be more diffuse or fuzzy than previously thought, with heavy elements mixed into the surrounding metallic hydrogen rather than forming a distinct solid center. This finding further emphasizes the continuous nature of Jupiter's interior structure. Understanding Jupiter's surfaceless nature helps us appreciate the diversity of planetary environments in our solar system and beyond. As we discover more exoplanets around other stars, many of which are gas giants similar to or larger than Jupiter, we must remember that our Earth-centric concept of a planetary surface isn't universal. Many worlds exist without anything we would recognize as ground beneath our feet, yet they are complete planetary systems with complex structures and dynamics. Jupiter's complex structure without a definite surface directly contributes to one of its most extreme characteristics: the crushing atmospheric pressure that would destroy any spacecraft attempting to venture too deeply into this giant world. This pressure environment is unlike anything we experience on Earth and represents one of the primary obstacles to exploration. The atmospheric pressure on Jupiter increases exponentially with depth. At the 1 bar reference level, what scientists conventionally call Jupiter's surface, the pressure is comparable to what we experience at sea level on Earth. But this familiar starting point quickly gives way to more extreme conditions. Just 50 kilometers below this point, the pressure already reaches about 2 bars. By 100 kilometers down, it surpasses 10 bars, equivalent to the pressure experienced about 100 meters deep in Earth's oceans. This is merely the beginning of Jupiter's pressure story. The rate at which pressure increases with depth on Jupiter is dramatically steeper than on Earth. By the time a hypothetical spacecraft has descended just 1,000 kilometers below the cloud tops, the pressure would reach approximately 1,000 bars, a level that would crush even the most reinforced deep-sea submersibles we've built for Earth's oceans. To put this in perspective, the deepest part of Earth's oceans, the Challenger, deep in the Mariana Trench, experiences pressures of about 1,100 bars. The most advanced deep-diving vessels humans have constructed can barely withstand these conditions. Yet this extreme pressure, which represents the absolute limit of Earth's natural environments, is found just a fraction of the way into Jupiter's atmosphere. Continue deeper, and the numbers become truly mind-boggling. At about 10,000 kilometers below the cloud tops, the pressure would exceed 1 million bars. At 20,000 kilometers deep, where hydrogen begins transitioning to its metallic state, pressures reach several millions of bars. These values exceed our everyday comprehension. They're hundreds of thousands of times greater than what we experience at Earth's surface. No material known to human engineering could withstand such pressures. Even the strongest alloys and composites would be compressed beyond their breaking points. Diamonds, among the most pressure-resistant materials we know, would be crushed in Jupiter's deeper layers. The hull of a spacecraft, regardless of how it was constructed, would collapse catastrophically long before reaching any significant depth in Jupiter's atmosphere. What makes these pressures particularly challenging is that they act uniformly from all directions. Unlike the directed pressure experienced by a submarine primarily from above, a spacecraft descending through Jupiter would be compressed equally from every side. This omnidirectional pressure eliminates any possibility of creating a structural design that could distribute or deflect the forces. The behavior of materials under such extreme pressures also becomes highly unpredictable. Materials don't simply break under these conditions. They undergo fundamental physical changes. Metals can become brittle or flow like liquids. Gases become so compressed that they behave like dense fluids. Electronic components, crucial for any spacecraft operation, would see their semiconductor properties altered, causing immediate failure of all systems. The Galileo probe, which represents our only direct sampling of Jupiter's atmosphere, was specially designed to withstand the entry pressures. Yet even this reinforced spacecraft only managed to survive to a depth where pressures reached about 22 bars, less than 1% of the way to Jupiter's centre. The probe was crushed and melted long before it could reach the more extreme regions of the planet. What's particularly fascinating about Jupiter's pressure environment is how it interacts with the planet's gases. Hydrogen and helium, which would be transparent gases under Earth conditions, become increasingly opaque as pressure rises. This creates a gradient of visibility. The deeper you go, the darker it becomes. Not because of lack of light sources, but because the compressed gas itself begins to block light transmission. The extreme pressure also affects the state of matter in Jupiter's atmosphere. The neat divisions we learn about on Earth, solid, liquid, gas, break down under Jovian conditions. Instead, we find substances existing in states that don't fit cleanly into these categories. The compressed hydrogen in Jupiter's mid-layers behaves neither exactly like a gas nor exactly like a liquid, but rather as a supercritical fluid with properties of both. Even more exotic is what happens at extreme depths. At approximately 20,000 kilometers below the cloud tops, where pressures reach millions of bars, hydrogen transitions into its metallic state. This isn't simply compressed hydrogen gas. It's a fundamentally different phase of the element, where the electrons are no longer bound to individual atoms, but move freely as they would in a metal. This metallic hydrogen, which doesn't naturally occur on Earth, conducts electricity and is responsible for generating Jupiter's powerful magnetic field. The pressure continues to increase all the way to Jupiter's core, which is estimated to experience pressures of about 70 million bars. At this depth, matter is compressed to densities difficult to replicate even in laboratory conditions on Earth. The core itself, believed to be composed of heavier elements like iron and silicates, exists in states that we can only theorize about based on computer models and limited experimental data. For spacecraft design, these pressure challenges appear insurmountable with current or near-future technology. Even if we could somehow solve the problems of temperature and corrosive chemicals, the pressure alone would prevent exploration of Jupiter beyond its outermost layers. The materials required to withstand millions of bars of pressure while maintaining functionality simply don't exist in our current engineering capabilities. The crushing atmospheric pressure of Jupiter serves as a stark reminder of how extreme conditions can become on other worlds, even within our own solar system. While we've designed spacecraft that can survive the vacuum of space and the harsh radiation environments near the Sun, the interior of Jupiter presents a fundamentally different challenge, one where the sheer force of compressed gases would overwhelm any human-made object. This reality doesn't mean Jupiter is completely unexplorable. Remote sensing techniques, like those employed by the Juno spacecraft currently orbiting Jupiter, allow us to study the planet's interior indirectly. By measuring subtle variations in Jupiter's gravity field, magnetic field, and atmospheric composition, scientists can infer details about the planet's internal structure without having to physically send probes into the crushing depths. As if the extreme pressures weren't challenging enough, Jupiter presents another equally formidable obstacle to exploration: its lethal temperature gradient. From freezing cold at the upper atmosphere to temperatures hotter than the Sun's surface at its core, this gradient creates an environment where no spacecraft could survive for long. The temperature profile of Jupiter begins with extreme cold. At the visible cloud tops, temperatures hover around -145 degrees Celsius. This is significantly colder than the coldest places on Earth, already presenting challenges for spacecraft components. which can become brittle and malfunction in such conditions. Many electronic systems, battery technologies, and propulsion mechanisms struggle to operate reliably at these temperatures. However, as a probe descends into Jupiter's atmosphere, it would experience a dramatic and continuous increase in temperature. Just 50 kilometers below the cloud tops, temperatures rise to approximately negative 80 degrees Celsius. By 100 kilometers down, the temperature approaches 0 degrees Celsius, roughly Earth's freezing point. This rapid warming continues as depth increases. By the time a hypothetical probe reached 1,000 kilometers below the cloud tops, the temperature would exceed several hundred degrees Celsius, hot enough to melt lead and damage most conventional spacecraft materials. This represents only the beginning of Jupiter's extreme thermal environment. The temperature gradient becomes even more dramatic with increasing depth. At 5,000 kilometers below the cloud tops, temperatures reach approximately 2,000 degrees Celsius, exceeding the melting point of most metals used in spacecraft construction, including titanium, which melts at about 1,668 degrees Celsius. No conventional spacecraft heat shield could protect against these conditions for more than a few moments. Deeper still, where hydrogen transitions to its metallic state at roughly 20,000 kilometers below the cloud tops, temperatures soar to around 10,000 degrees Celsius. For comparison, the surface of the Sun is about 5,500 degrees Celsius, meaning that Jupiter's interior is nearly twice as hot as the visible surface of our star. At Jupiter's core, temperatures are estimated to reach an astonishing 24,000 degrees Celsius. At this temperature, even materials that remain solid on Earth under extreme conditions would exist as gases or plasmas. These temperatures are comparable to those found in the outer layers of hotter stars. What makes Jupiter's thermal gradient particularly challenging for exploration is the combination of heat with pressure. On Earth, we have technologies that can briefly withstand extremely high temperatures, like the heat shields on spacecraft designed for atmospheric re-entry, which can handle temperatures up to about 2,000 degrees Celsius. However, these technologies rely on ablation, the controlled burning away of material, or radiative cooling to function. In Jupiter's atmosphere, these heat management strategies would fail. The high-pressure environment prevents effective ablation, as there's nowhere for the vaporized material to escape to. Meanwhile, radiative cooling becomes ineffective because the surrounding atmosphere is already superheated, providing no temperature gradient to dissipate heat into. A spacecraft would essentially be surrounded by an ever-hotter oven with no way to release the accumulating thermal energy. The thermal challenges are compounded by the nature of heat transfer in Jupiter's dense atmosphere. On Earth or in space, spacecraft primarily manage heat through radiation or limited convection in the thin atmosphere. Within Jupiter's increasingly dense layers, heat transfer through convection becomes extraordinarily efficient and intense. This means a spacecraft wouldn't just be sitting in hot surroundings, it would be actively and rapidly heated from all directions by the highly conductive atmospheric gases. This heating would affect different spacecraft materials at different rates, creating additional structural problems. Materials expand when heated, but they do so at different rates. In a complex spacecraft with components made of various metals, ceramics, and composites, these differential expansion rates would quickly cause joints to fail, seals to break, and structural integrity to collapse, even before the absolute temperature limits of individual materials were reached. The Galileo probe, our only direct sampling mission to Jupiter, was equipped with a heat shield made of carbon phenolic, the same material used on nuclear warhead nose cones, capable of withstanding extreme temperatures during brief exposures. Even with this advanced thermal protection, the probe survived for only 58 minutes before its systems failed. The heat shield was designed primarily to handle the initial entry heating, not the sustained environmental heat of Jupiter's deeper atmosphere. It's worth noting that the thermal gradient presents a cruel paradox for Jupiter exploration. The upper atmosphere is cold enough to cause certain systems to fail due to low temperature effects on electronics and mechanical components. Yet designing a spacecraft that can handle these frigid conditions would likely make it even more vulnerable to the extreme heat encountered just a few hundred kilometers deeper. Any thermal insulation designed to keep components warm in the upper atmosphere would trap the increasing heat as the probe descended, accelerating its destruction. For human-made technology, this combination of rising temperatures and increasing pressures creates a zone of certain destruction. Even if we could somehow engineer materials to withstand the crushing pressures, the extreme heat would melt or vaporize them. Conversely, even if we could develop cooling systems to manage the heat, the pressure would crush such systems before they could operate effectively. The temperature gradient also affects the chemistry of Jupiter's atmosphere. At various depth-dependent temperature thresholds, different chemical reactions become possible, creating layers with distinct chemical compositions. Some of these reactions would be highly corrosive to spacecraft materials, adding chemical degradation to the list of thermal challenges. Current materials science offers no solutions to these combined thermal and pressure challenges. The most advanced heat-resistant materials known, such as certain ceramics that can briefly withstand temperatures up to 3,000 degrees Celsius, would still fail catastrophically in Jupiter's mid-depth regions, and that's before considering the pressure effects. Beyond the crushing pressures and extreme temperatures, Jupiter presents another lethal challenge to any spacecraft: hypersonic winds that would tear apart even the most robust human-made structures. The wind systems of Jupiter are nothing like those we experience on Earth, operating on scales and at speeds that defy our terrestrial understanding of atmospheric circulation. Jupiter's visible atmosphere is organized into distinct bands called zones and belts that encircle the entire planet. These alternating light and dark bands aren't just different in color, they represent massive wind currents moving in opposite directions. The boundaries between these bands, known as zonal jets, feature some of the strongest sustained winds in the solar system. At their fastest, Jupiter's zonal jets reach speeds of approximately 650 kilometers per hour. For comparison, the most destructive hurricanes on Earth rarely sustain winds beyond 300 kilometers per hour. Even more impressively, while Earth's fastest winds occur in relatively small, short-lived storm systems, Jupiter's high-speed winds persist continuously in bands that stretch tens of thousands of kilometers around the planet. What makes these winds particularly dangerous for spacecraft isn't just their speed, but their consistency and extent. On Earth, even in the most violent storms, wind speeds vary considerably with height and location, offering potential refuge from the strongest gusts. Jupiter offers no such respite. Its wind bands maintain their extreme velocities across vast regions of the planet. The boundary regions between adjacent bands create enormous shear forces. Imagine a spacecraft descending through Jupiter's atmosphere and encountering a region where the wind above is moving east at 500 kilometers per hour, while the wind below is moving west at the same speed. This 1,000 km per hour velocity differential across a relatively short vertical distance would subject the craft to torsional forces that would twist and ultimately disintegrate its structure. These wind shear zones aren't static either. They oscillate in position and intensity, creating unpredictable turbulent regions that no current spacecraft design could navigate safely. The turbulence in Jupiter's atmosphere operates on scales much larger than on Earth, with eddies and vortices that can be larger than our entire planet, but also extends down to microscopic scales with intense, small-scale turbulence. The physical effect of these winds on a spacecraft would be devastating. The aerodynamic forces would create vibrations at frequencies that could match the structural resonance of spacecraft components, amplifying the mechanical stress until materials reach their breaking point. Spacecraft are typically designed to withstand the smooth, predictable forces of launch and re-entry, not the chaotic, multidirectional stresses of Jupiter's turbulent atmosphere. These destructive winds exist throughout Jupiter's atmosphere, but vary with depth. In the upper atmosphere, the east-west zonal jets dominate the wind pattern. Deeper down, where the atmosphere becomes denser, three-dimensional circulation patterns develop. with powerful updrafts and downdrafts adding vertical components to the already formidable horizontal winds. These vertical currents can reach speeds of several hundred kilometers per hour, creating additional stresses on any descending craft. Beyond the direct mechanical forces, Jupiter's winds pose another danger: particulate bombardment. The atmosphere contains various substances: ammonia ice, ammonium hydrosulfide, water ice, and possibly silicates and other materials, suspended as tiny particles. At wind speeds of hundreds of kilometers per hour, these particles become microscopic projectiles that would continuously bombard a spacecraft's exterior. This particulate bombardment would cause rapid erosion of external surfaces, including sensors, communications equipment, and thermal protection systems. The Galileo probe, during its brief descent, recorded instances of particle impacts that were more numerous and energetic than expected. Over time, this erosion would compromise critical spacecraft systems long before pressure or temperature effects became lethal. The winds also create powerful electrostatic environments. The movement of particles in Jupiter's atmosphere generates substantial electrical charges, much like how storms on Earth produce lightning, but on a vastly larger scale. Jupiter experiences lightning bolts up to 1,000 times more powerful than Earth's, which could easily disable or destroy spacecraft electronics. The combination of these wind effects, direct aerodynamic forces, shear stresses, turbulence, particulate erosion, and electrical discharges, creates an environment where no current spacecraft technology could survive for extended periods. Even if we could somehow engineer solutions for the pressure and temperature challenges, the wind forces alone would limit exploration to the most superficial layers of Jupiter's atmosphere. Jupiter's wind systems also create unique computational challenges for mission planning. The complex fluid dynamics of the atmosphere, coupled with the planet's rapid rotation, one day on Jupiter is just under 10 hours, make it extremely difficult to predict exact conditions at specific locations and times. This unpredictability means that spacecraft trajectories through the atmosphere would be nearly impossible to plan with precision, further complicating any attempt at exploration. Scientists have considered various designs that might better withstand Jupiter's winds, including spherical probes that would offer no preferred direction for wind forces to act upon. However, even these optimized shapes would eventually succumb to the combined effects of aerodynamic stresses and particulate erosion. The fundamental problem remains that materials strong enough to withstand these conditions for extended periods simply don't exist in our current engineering capabilities. When discussing the extreme wind conditions on Jupiter, no feature is more iconic or more dangerous than the Great Red Spot, a massive storm system that has persisted in Jupiter's southern hemisphere for at least 400 years, and likely much longer. This colossal anticyclonic storm represents perhaps the most hostile environment for a spacecraft in our solar system outside the Sun itself. The Great Red Spot is truly enormous, at approximately 16,000 kilometers across. It could comfortably fit the entire Earth within its boundaries. Despite having shrunk somewhat from its historical maximum, when it was about twice Earth's diameter, it remains the largest and longest-lived storm known in our solar system. Its red coloration, which varies in intensity over time, is believed to come from complex organic compounds and possibly phosphorus-containing molecules brought up from deeper layers of the atmosphere. As an anticyclonic storm in the southern hemisphere, the Great Red Spot rotates counterclockwise, with a complete rotation taking about 6 Earth days. This relatively slow rotation compared to its size creates a deceptive impression of calmness when observed from Earth or from orbit. In reality, it's an environment of exceptional violence. The wind speeds in the Great Red Spot reach their maximum at the periphery of the storm, where they can exceed 400 kilometers per hour as they circulate around the calmer central region. These peripheral winds form a boundary that effectively isolates the storm's interior from the surrounding atmosphere. contributing to its remarkable longevity. What makes the Great Red Spot particularly dangerous for spacecraft isn't just the horizontal wind speed, but the complex, three-dimensional circulation within it. The storm features powerful updrafts in its center that lift gases from lower, warmer regions of Jupiter's atmosphere. These rising currents can reach vertical speeds of hundreds of kilometers per hour, creating a central region where pressure and temperature conditions differ significantly from the surrounding atmosphere at the same altitude. As these gases rise and cool, they move outward toward the periphery of the storm, where they eventually sink back to lower altitudes. This circulation pattern creates a dome-like structure that actually protrudes above the surrounding cloud tops by about 8 kilometers, making the Great Red Spot visible as a raised feature when Jupiter is viewed from the side. Any spacecraft entering this massive storm system would experience rapidly changing wind directions and speeds that would create unpredictable and overwhelming stresses on its structure. The transitions between different flow regions within the storm, from the relatively calm center to the high-speed periphery, or from horizontal to vertical flow, would subject the craft to sudden acceleration forces from multiple directions simultaneously. The Great Red Spot also creates unique thermal conditions. The upwelling of gases from deeper, warmer regions means that the interior of the storm is actually warmer than the surrounding atmosphere at the same altitude. These temperature differentials create additional mechanical stresses on materials as they expand and contract in response to rapid temperature changes. The fluid dynamics within the Great Red Spot are so complex that even our most sophisticated atmospheric models struggle to fully simulate its behavior. Recent observations from NASA's Juno spacecraft have revealed previously unknown structures within the storm, including nested cyclones and unexpected vertical features extending far deeper into the atmosphere than previously thought. This complexity makes the storm system essentially unpredictable for spacecraft navigation purposes. Particularly dangerous are the gravity waves generated by the Great Red Spot. These aren't gravitational waves in the sense of Einstein's relativity, but rather oscillations in the atmosphere caused by the interplay of gravity and buoyancy forces. The Great Red Spot generates powerful gravity waves that propagate both horizontally and vertically through Jupiter's atmosphere, creating additional turbulence far from the storm itself. The Juno mission has provided new insights into the depth of the Great Red Spot, revealing that it extends at least 300 to 500 kilometers below the visible cloud tops, much deeper than previously thought. This means the storm affects a substantial vertical column of Jupiter's atmosphere, with different conditions at different depths, all hostile to spacecraft survival. Particulate matter within the Great Red Spot presents another hazard. The storm's powerful circulation patterns concentrate various chemical compounds, creating localized regions with higher concentrations of potentially corrosive substances. These materials, carried at high velocity by the storm's winds, would accelerate the erosion of spacecraft surfaces beyond even the already severe rates in Jupiter's regular atmosphere. The electromagnetic environment within the Great Red Spot adds yet another layer of hostility for spacecraft. The complex fluid movements generate electrical charges and localized magnetic field anomalies that could interfere with spacecraft electronics and navigation systems. Some observations suggest that lightning activity might be enhanced within and around the storm system, presenting additional risks for sensitive equipment. Perhaps most concerningly from an exploration perspective, the Great Red Spot represents a dynamic and evolving threat. Despite its long-term stability as a feature, the storm undergoes significant changes in size, shape, and intensity over time scales of months to years. This means that data gathered about the storm during one mission might not accurately represent conditions encountered during a subsequent mission, making planning for its hazards particularly challenging. The combination of extreme winds, complex circulation patterns, temperature differentials, concentrated chemical compounds, and electromagnetic anomalies makes the Great Red Spot effectively a perfect storm of spacecraft-destroying conditions. Even if we develop technology that could survive Jupiter's general atmospheric conditions, the Great Red Spot would remain an essentially impassable region for direct exploration with foreseeable technology. While the Great Red Spot demonstrates the mechanical dangers of Jupiter's atmosphere, even before a spacecraft would face these wind systems, it would encounter another formidable obstacle: Jupiter's enormous magnetic field. This invisible but incredibly powerful force extends millions of kilometers into space and would severely impact any technology approaching or attempting to explore the planet. Jupiter's magnetic field is the strongest of any planet in our solar system, approximately 14 times stronger than Earth's. This tremendous field is generated by electrical currents in Jupiter's rapidly rotating metallic hydrogen layer, creating a magnetosphere so vast that it extends up to 7 million kilometers toward the Sun and stretches in a tail that reaches the orbit of Saturn, more than 650 million kilometers away. The sheer scale of this magnetic environment is difficult to comprehend. If Jupiter's magnetosphere were visible to the naked eye from Earth, it would appear larger in our sky than the full moon, despite being hundreds of millions of kilometers away. This enormous magnetic bubble interacts with the solar wind, the stream of charged particles flowing from the Sun, creating complex structures including a bow shock, magnetosheath, and elongated magnetotail, similar to Earth's magnetic field but on a drastically larger scale. For spacecraft approaching Jupiter, the effects of this powerful magnetic field begin long before reaching the planet itself. As a craft crosses into Jupiter's magnetosphere, typically around 3 million kilometers from the planet, it immediately experiences dramatically increased flux of charged particles trapped in the magnetic field. These particles induce electrical currents in any conductive materials, potentially disrupting or damaging sensitive electronic systems. The situation becomes increasingly hazardous as a spacecraft approaches closer to Jupiter. The rapidly rotating magnetic field Jupiter completes a rotation in just under 10 hours, sweeps through space, carrying with it enormous electrical currents. These currents flow along magnetic field lines between the planet and its moons, particularly Io, creating a circuit that carries approximately 1 trillion watts of power, equivalent to all of human civilization's power generation many times over. This dynamic electromagnetic environment poses several specific threats to spacecraft. First, the strong and rapidly changing magnetic field induces electrical currents in any conductive components. These induced currents can overwhelm and damage electronic circuits, corrupt computer memory, and cause unexpected behavior in spacecraft systems, even with specialized shielding. The extreme strength of Jupiter's magnetic field makes these effects difficult to mitigate completely. Second, the magnetic field creates significant mechanical forces on any conductive materials. As a spacecraft moves through Jupiter's magnetic field, the interaction between the field and any induced electrical currents generates forces that can physically stress components. While these forces are relatively weak compared to atmospheric effects, they represent an additional stress on spacecraft systems over extended periods. Third, and perhaps most challenging, Jupiter's magnetic field traps charged particles in radiation belts similar to Earth's Van Allen belts, but immensely more intense. These radiation belts contain high-energy electrons, protons, and heavier ions that can penetrate spacecraft shielding and damage electronic components. The radiation levels are so extreme that they affected mission design for previous Jupiter missions like Galileo and currently influence operations of the Juno spacecraft. The magnetic field strength varies significantly with location around Jupiter. It's strongest near the poles, where the magnetic field lines converge, creating regions of particularly intense radiation and electromagnetic effects. The field also exhibits significant asymmetries and localized anomalies that make predicting exact conditions at specific locations challenging for mission planners. Particularly notable is the interaction between Jupiter's magnetic field and its moon Io. Volcanic activity on Io ejects material that becomes ionized and forms a plasma torus around Jupiter. This plasma, trapped by the magnetic field, creates a region of especially hazardous radiation called the Io plasma torus. Any spacecraft passing through this region faces enhanced radiation exposure beyond the already extreme background levels. The electromagnetic environment becomes even more complex in Jupiter's inner atmosphere. As a spacecraft would descend toward the cloud tops, it would encounter increasingly dense plasma, electrically charged gas, that interacts strongly with the magnetic field. These interactions generate powerful electrical currents and localized magnetic disturbances that would further compromise spacecraft systems. Additionally, Jupiter experiences the most powerful lightning storms in the solar system, with lightning bolts up to 1,000 times more energetic than Earth's. These lightning discharges, enhanced by the strong background magnetic field, create electromagnetic pulses that could disable or destroy spacecraft electronics, similar to the effects of a nuclear EMP but occurring naturally and frequently. For any craft attempting to penetrate deep into Jupiter's atmosphere, the combination of the intense magnetic field and the increasingly conductive atmospheric gases would create a condition similar to putting electronic equipment inside an active microwave, inducing currents that would rapidly heat conductive components from the inside out, causing catastrophic failure. Jupiter's powerful magnetic field also presents communication challenges for any probe sent to explore the planet. Radio signals, which spacecraft use to transmit data back to Earth, can be distorted, attenuated, or completely blocked by the complex plasma environments created by the interaction of the magnetic field with charged particles. This means that even if a probe could somehow survive the other hazards, it might be unable to transmit its findings back to Earth. Even orbital missions around Jupiter must be carefully designed to minimize exposure to the worst effects of the magnetic field. The Juno spacecraft, currently studying Jupiter, follows a highly elliptical polar orbit that passes over Jupiter's poles and keeps the craft out of the most intense radiation belts for most of its orbit. Even with this careful trajectory planning and extensive radiation shielding, Juno's instruments and electronics are gradually degrading due to radiation exposure. The challenges posed by Jupiter's magnetic field highlight a fundamental obstacle to exploring the giant planet. Even before encountering the atmospheric hazards, any spacecraft would have to survive an electromagnetic environment hostile enough to disable or destroy conventional electronics. This magnetic barrier serves as the first line of Jupiter's many defenses against human exploration efforts. As if Jupiter's magnetic field weren't challenging enough, it creates an even more immediately destructive environment through the extreme radiation it generates. This radiation environment exceeds anything encountered elsewhere in our solar system except the immediate vicinity of the Sun and represents perhaps the most significant obstacle to exploring Jupiter with current technology. Jupiter's radiation belts are formed when charged particles, primarily electrons and protons, become trapped by the planet's powerful magnetic field. These particles spiral along magnetic field lines, bouncing back and forth between the northern and southern hemispheres while also drifting around the planet. As they travel, they're accelerated to enormous energies, creating belts of high-energy radiation that surround Jupiter. The intensity of this radiation is staggering. At certain locations within Jupiter's magnetosphere, particularly in the inner radiation belts, radiation levels can exceed 50 million rads, roughly 10,000 times the dose that would be lethal to a human. Even robotic spacecraft, designed to be far more radiation tolerant than humans, struggle to survive in this environment. To put these radiation levels in perspective, consider that a typical human on Earth receives about 0.3 to 0.4 rems of radiation per year from natural background sources. A dose of 400 to 500 rems over a short period would likely be fatal. In Jupiter's inner radiation belts, an unshielded human would receive a lethal dose in fractions of a second, and even with the best practical radiation shielding, survival time would be measured in minutes at most. For electronic components, the situation is similarly dire. Radiation affects electronics in several ways, all potentially fatal to spacecraft operation. First, Total ionizing dose effects gradually degrade semiconductor materials as radiation displaces atoms and creates defects in the crystal structure over time. This causes transistors to change their operating characteristics, leading to circuit malfunction. Second, single event effects occur when a high-energy particle strikes a sensitive node in an electronic component, depositing enough energy to change the state of memory cells, trigger spurious signals, or even cause permanent damage through burnout of power transistors. In Jupiter's radiation environment, these events would occur at rates thousands of times higher than in Earth orbit, overwhelming even the most robust error correction systems. Third, displacement damage occurs when radiation physically knocks atoms out of their positions in semiconductor crystal lattices, permanently degrading device performance. This effect is particularly problematic for solar cells, sensors, and optical components, which would rapidly lose efficiency in Jupiter's radiation environment. The radiation situation becomes progressively worse as a spacecraft approaches Jupiter. At a distance of 1 million kilometers, radiation levels are already concerning but manageable with heavy shielding. By the time a craft reaches Jupiter's innermost moon, Io, approximately 420,000 kilometers from Jupiter, radiation levels are severe enough to cause rapid degradation of spacecraft systems. And near Jupiter's cloud tops, radiation reaches levels that would disable conventional electronics in minutes to hours, even with substantial shielding. The distribution of radiation around Jupiter isn't uniform. The radiation belts are shaped by the planet's magnetic field, creating regions of particularly intense radiation, especially near the magnetic equator. Jupiter also has a radiation hotspot known as the Io plasma torus, a donut-shaped region of intense radiation that follows the orbit of the moon Io. This region contains particularly high fluxes of heavy ions, which cause enhanced radiation damage compared to electrons or protons of similar energy. Previous missions to Jupiter have had to employ various strategies to cope with this hostile radiation environment. The Galileo spacecraft, which orbited Jupiter from 1995 to 2003, received a total radiation dose more than 2 times its design limit, causing numerous anomalies and failures during its extended mission. The more recent Juno spacecraft incorporates a radiation vault, a titanium box with walls a centimeter thick to protect its most sensitive electronics. Even with this protection, Juno's instruments are gradually degrading, limiting the mission's potential lifetime. For any spacecraft attempting to descend into Jupiter's atmosphere, the radiation challenges would be even more severe. As the craft approached the planet, it would pass through increasingly intense regions of the radiation belts. By the time it reached the upper atmosphere, its electronic systems would already have absorbed substantial radiation damage, potentially compromising critical functions before atmospheric entry even began. The radiation also affects materials beyond just electronics. Many structural materials experience embrittlement when exposed to high radiation doses, becoming more prone to cracking and failure under stress. Polymers, used in everything from wire insulation to thermal blankets, can break down, becoming brittle or even crumbling under intense radiation exposure. Optical materials like lenses and windows can darken as radiation creates color centers in the glass, potentially blinding a spacecraft's cameras and sensors. Certain specialized technologies are particularly vulnerable to radiation effects. For example, the miniaturized electronics that enable modern small spacecraft are generally more radiation sensitive than older, larger components. Advanced high-density batteries can experience internal shorts when exposed to heavy ion radiation. Even supposedly radiation-hard systems have failure modes when radiation levels exceed their design specifications by orders of magnitude, as would happen near Jupiter. The radiation challenge extends to communications as well. The ionized particles in Jupiter's magnetosphere can scatter and absorb radio waves, creating unpredictable interference that complicates communication with Earth. This means that even if a probe somehow survived the radiation long enough to gather data about Jupiter, transmitting that information back might prove impossible from certain locations within the magnetosphere. Perhaps most troubling from an exploration perspective is that radiation damage is cumulative and often unpredictable. A spacecraft might function normally until suddenly crossing a threshold where multiple systems fail simultaneously. This unpredictability makes radiation one of the most insidious hazards of Jupiter exploration, as a probe could be functioning perfectly one moment and completely disabled the next without obvious warning signs. The extreme radiation environment effectively creates a boundary beyond which conventional spacecraft cannot operate for extended periods. This boundary lies well above Jupiter's atmosphere, meaning that even before encountering the atmospheric hazards we've discussed, the crushing pressure, extreme temperatures, and violent winds, a spacecraft would already be fighting a losing battle against radiation-induced degradation. Current shielding technology simply cannot provide sufficient protection for extended operation in Jupiter's most intense radiation regions. The mass required for adequate shielding would make any mission impractical with current launch capabilities. And while future technologies might improve radiation hardness of electronics, the fundamental physics of radiation interaction with matter places limits on how much improvement is possible. This radiation barrier represents yet another reason why exploring Jupiter's depths remains beyond our current technological capabilities, beyond the invisible but deadly radiation. Any spacecraft venturing into Jupiter would face yet another destructive force, the planet's highly corrosive chemical composition. Jupiter's atmosphere might seem simple at first glance, primarily hydrogen and helium, but it contains a complex mixture of reactive compounds that would aggressively attack spacecraft materials, particularly at the high temperatures and pressures found deeper in the atmosphere. The outermost layers of Jupiter's atmosphere contain several chemically active compounds known to be corrosive to spacecraft materials. Ammonia, NH3, makes up about 0.1% of Jupiter's atmosphere, but plays an outsized role in its corrosive potential. At the low temperatures in Jupiter's upper atmosphere, ammonia forms ice crystals. But as a spacecraft descends and temperatures increase, it becomes a reactive gas and eventually a supercritical fluid under high pressure. Ammonia readily attacks copper and copper-containing alloys, which are common in spacecraft electronics and wiring. It also reacts with many polymer materials used for insulation and seals. Another corrosive compound is hydrogen sulfide, H2S, present in smaller quantities but extraordinarily damaging to spacecraft materials. Even in low concentrations, hydrogen sulfide aggressively attacks most metals, forming metal sulfides that compromise structural integrity. It's particularly damaging to silver and copper components, which would be rapidly tarnished and degraded. Hydrogen sulfide also poses a serious threat to many sensor types, particularly those with exposed metal films or contacts. Water, which makes up about 0.4% of Jupiter's atmosphere, might seem harmless, but under Jovian conditions, it becomes highly reactive. As a spacecraft descends into regions where temperatures exceed 100 degrees Celsius but remains under enormous pressure, water exists as a supercritical fluid with enhanced solvent properties. This supercritical water can dissolve compounds that normal water cannot, accelerating corrosion processes. It can also penetrate tiny cracks and pores in materials, causing internal corrosion that wouldn't occur under normal conditions. Deeper in Jupiter's atmosphere, methane, CH4, and other hydrocarbons become more abundant. At the extreme temperatures and pressures found in Jupiter's lower atmosphere, these normally stable molecules can break down and reform into more reactive compounds. These reactive hydrocarbons can attack polymer components, causing them to swell, soften, or disintegrate entirely. Many of the elastomers used for seals in spacecraft are particularly vulnerable to this type of chemical attack. The corrosive effects of these compounds are dramatically enhanced by Jupiter's extreme environmental conditions. High temperatures accelerate chemical reaction rates. A common rule of thumb suggests reaction rates double with each 10 degrees Celsius increase in temperature. Given that temperatures rise from negative 145 degrees Celsius at the cloud tops to thousands of degrees deeper in the atmosphere, reaction rates would increase by many orders of magnitude as a spacecraft descends. The high pressures in Jupiter's atmosphere further enhance corrosive processes. Increased pressure can force reactive gases into materials, including through microscopic defects that would normally be impenetrable. This pressure-driven infiltration accelerates corrosion from the inside out, compromising structural integrity before external signs become visible. Perhaps most challenging from a materials perspective is hydrogen embrittlement, a process specific to hydrogen-rich environments like Jupiter's atmosphere. When molecular hydrogen, H2, comes into contact with metals under pressure, it can dissociate into atomic hydrogen, which is small enough to penetrate the crystalline structure of many metals. Once inside the metal lattice, hydrogen atoms collect at defects, creating internal pressure that ultimately leads to cracking. This process affects even high-strength alloys designed for extreme environments, including many titanium and nickel-based superalloys used in aerospace applications. The combination of these corrosive processes would attack a spacecraft from multiple directions simultaneously. External surfaces would face direct chemical attack from ammonia, hydrogen sulfide, and other reactive gases. Seals and gaskets would be compromised by exposure to hydrocarbons and supercritical fluids. Structural metals would suffer from hydrogen embrittlement, becoming brittle and prone to catastrophic failure. Electronic components, if somehow protected from direct chemical exposure, would still eventually fail as corrosive agents penetrated their protective enclosures. Spacecraft designers have developed various protective strategies for corrosive environments. But Jupiter presents a unique challenge because the corrosive agents are so diverse. Materials resistant to ammonia might be vulnerable to hydrogen sulfide. Coatings that protect against sulfur compounds might break down under exposure to supercritical water. The multifaceted chemical attack makes developing comprehensive protection nearly impossible. Furthermore, any protective coatings or barriers would be simultaneously challenged by the extreme temperatures, pressures, and mechanical stresses of Jupiter's atmosphere. A protective layer might work perfectly under laboratory conditions but fail rapidly when subjected to the combined chemical, thermal, and mechanical stresses of actual Jovian conditions. The Galileo probe, which represents our only direct sampling of Jupiter's atmosphere to date, wasn't designed to withstand these chemical conditions for long. Its primary protection against the chemical environment was simply the brevity of its mission. It was expected to function for only about 60 minutes before being destroyed by other factors like heat and pressure. Even with this limited exposure time, the probe's instruments detected higher than expected levels of certain reactive species, suggesting that our understanding of Jupiter's atmospheric chemistry still has significant gaps. For a hypothetical long-duration mission to Jupiter's deeper atmosphere, the chemical environment presents a seemingly insurmountable challenge with current materials technology. Even advanced corrosion-resistant materials like gold, platinum, or certain ceramics would eventually succumb to the combined effects of reactive chemicals under Jupiter's extreme temperatures and pressures. This chemical hostility adds yet another reason why Jupiter's depths remain inaccessible to current human technology. Our most direct encounter with Jupiter's hostile environment came on December 7th, 1995, when the Galileo atmospheric probe plunged into the giant planet. This ambitious mission provided our only in situ measurements of Jupiter's atmosphere and demonstrated just how quickly the planet's conditions destroy human-made objects. The lessons from this mission offer crucial insights into why Jupiter's interior remains one of the most inaccessible places in our solar system. The Galileo atmospheric probe was a remarkable feat of engineering, a 139-kilogram cone-shaped craft designed specifically to survive entry into Jupiter's atmosphere and transmit data for as long as possible before being destroyed. launched from the main Galileo spacecraft. The probe was essentially a sacrificial explorer, designed to gather as much information as possible during its brief lifetime. The probe's journey began with one of the most extreme atmospheric entries ever attempted. Hitting Jupiter's upper atmosphere at a speed of approximately 47 kilometers per second, the probe experienced deceleration forces reaching 230 Gs, far beyond what any human could survive. These forces were more than twice what mission designers had anticipated, immediately highlighting how our models of Jupiter's atmosphere were incomplete. To withstand the intense heat of atmospheric entry, the probe was equipped with a carbon phenolic heat shield, the same material used for nuclear warhead re-entry vehicles. During entry, temperatures on the heat shield reached about 16,000 degrees Celsius, twice as hot as the surface of the Sun. Despite these extreme conditions, the heat shield performed its job, allowing the probe's scientific instruments to begin operating as planned. After the initial entry phase, the heat shield was jettisoned, and the probe deployed a parachute to slow its descent through the atmosphere. This began the probe's brief window of scientific data collection, which lasted just 58 minutes before contact was lost. During this short period, the Galileo probe transmitted invaluable data about Jupiter's atmosphere back to the main spacecraft, which then relayed the information to Earth. The probe's suite of instruments measured temperature, pressure, wind speed, atmospheric composition, cloud properties, dot, and radiation levels as it descended approximately 160 kilometers into Jupiter's atmosphere. The data revealed several surprises that challenged existing models of Jupiter's structure and composition. One of the most unexpected findings was the relative absence of water in the region the probe sampled. Scientists had expected Jupiter's atmosphere to contain significant amounts of water, but the probe found much less than anticipated. This finding remains somewhat controversial, with many scientists believing the probe simply happened to enter a particularly dry region of Jupiter's atmosphere, possibly a local weather phenomenon similar to a desert region on Earth. The probe also measured unexpectedly strong winds that remained constant or even increased with depth. Prior to the mission, scientists had generally believed that Jupiter's wind speeds would decrease as the atmosphere became denser. Instead, the probe found winds of about 700 kilometers per hour that showed no signs of diminishing during its descent. This suggested that Jupiter's powerful atmospheric circulation extends much deeper than previously thought, driven by heat from the planet's interior rather than solely by solar energy as on Earth. In terms of composition, the probe confirmed that Jupiter's atmosphere is primarily hydrogen and helium, but also detected unexpected concentrations of certain heavy elements. The abundances of elements like carbon, sulfur, and nitrogen were found to be higher than solar values, providing important clues about the formation of Jupiter and the early solar system. Perhaps most importantly, the Galileo probe demonstrated the rapid progression of hostile conditions within Jupiter's atmosphere. When the probe began transmitting data, it was experiencing temperatures of about negative 150 degrees Celsius and pressures less than 1/10 of Earth's atmospheric pressure at sea level. By the time communication was lost 58 minutes later, the temperature had risen to about 150 degrees Celsius, and the pressure had increased to more than 20 times Earth's atmospheric pressure. The probe didn't transmit the cause of its own destruction, but scientists believe it was likely a combination of factors that overwhelmed its systems nearly simultaneously. The rising temperature would have eventually exceeded the operating limits of its electronic components. The increasing pressure would have crushed its structure, and the probe's battery power would have been depleted as it worked to transmit data through the increasingly dense atmosphere. What's particularly sobering about the Galileo probe's fate is that it was destroyed after penetrating less than 1% of the distance to Jupiter's theoretical center. The probe descended approximately 160 kilometers, while Jupiter's radius is about 70,000 kilometers. The conditions that destroyed this specially designed probe in less than an hour represent just the very outermost fringes of Jupiter's atmosphere. with far more extreme conditions lying deeper. The brief lifetime of the Galileo probe highlights the enormous technological challenges of exploring Jupiter's interior. Despite being designed specifically for this hostile environment and incorporating the most advanced materials and technologies available at the time, the probe survived only long enough to sample the thinnest outer layers of the planet's atmosphere. The Galileo mission also demonstrated the difficulty of communicating through Jupiter's atmosphere. As the probe descended, its radio signal became increasingly attenuated by the thickening atmosphere. Even with the main Galileo spacecraft positioned to receive transmissions, maintaining reliable communication proved challenging. Any future mission attempting to probe deeper would face even more severe communication limitations, potentially preventing the transmission of data back to Earth. Despite its brief lifetime, the Galileo probe provided our most direct glimpse into the hostile conditions of Jupiter's atmosphere. The mission confirmed that Jupiter becomes progressively more inhospitable with depth at rates that match or exceed theoretical predictions. The probe's quick destruction serves as a sobering reminder of the extreme conditions that prevent us from exploring deeper into the giant planet with current technology. Even with 25 years of technological advancement since the Galileo mission, we remain far from developing systems that could penetrate significantly deeper into Jupiter's increasingly hostile interior. The fate of the Galileo probe highlights not just the atmospheric conditions of Jupiter, but also a fundamental challenge that makes exploring the gas giant so difficult: the limitations of material science under such extreme conditions. As we develop spacecraft for different environments throughout the solar system, we're constantly pushing the boundaries of what our materials can withstand. But Jupiter presents a unique combination of stresses that exceeds the capabilities of any known material. Traditional aerospace materials like aluminum alloys begin to fail at relatively modest conditions compared to what Jupiter presents. Aluminum, commonly used in spacecraft structures, starts to lose its strength at just 150 degrees Celsius and would melt entirely at around 660 degrees Celsius, temperatures reached fairly early in a descent through Jupiter's atmosphere. High-strength steel alloys retain their properties to higher temperatures but would still become soft and deform under the increasing pressures, long before reaching significant depths. More exotic materials like titanium and its alloys offer better temperature resistance, maintaining useful strength up to about 500 degrees Celsius and melting around 1,668 degrees Celsius. But even these advanced materials would quickly reach their limits as both temperature and pressure increase during descent. The problem is compounded because materials generally become weaker as they get hotter, making them more vulnerable to Jupiter's crushing pressures precisely when they need to be strongest. Heat shields designed for planetary entry, like the carbon phenolic used on the Galileo probe, can temporarily withstand temperatures up to 3,500 degrees Celsius. However, these materials work by slowly ablating, essentially burning away in a controlled manner to carry heat away from the spacecraft. In Jupiter's atmosphere, the combination of pressure-preventing effective ablation and the extended exposure time would render such materials ineffective beyond the initial entry phase. Modern composite materials, including carbon fiber reinforced polymers used in advanced aerospace applications, offer excellent strength-to-weight ratios under Earth conditions. However, these materials begin to degrade at relatively low temperatures compared to Jupiter's interior. The polymer matrices typically start to break down around 200 to 300 degrees Celsius, long before reaching the more extreme depths of Jupiter's atmosphere. Ceramics and ceramic composites, among the most heat-resistant materials available, can maintain their properties at temperatures up to 1,500 degrees Celsius or more. Materials like silicon carbide and certain ultra-high temperature ceramics might withstand the thermal environment somewhat deeper into Jupiter. However, ceramics are typically brittle and vulnerable to the mechanical stresses created by Jupiter's turbulent atmosphere. The rapid pressure changes and atmospheric buffeting would likely cause ceramic components to crack and fail. The real challenge of Jupiter isn't just the extreme values of individual factors, but their combination. A material might withstand high temperatures in a laboratory on Earth, but that same material under simultaneous high pressure, chemical attack, and mechanical stress behaves very differently. Jupiter creates a perfect storm of material degradation mechanisms that work synergistically to break down any substance. Under extreme pressures, materials undergo fundamental changes in their physical properties. Crystal structures can reorganize, electron shells can be compressed, and materials that are normally solid can begin to flow like liquids. These changes occur because the spacing between atoms is forcibly decreased, altering the fundamental nature of chemical bonds. Materials science has limited data on how conventional engineering materials behave under pressures reaching millions of times Earth's atmospheric pressure, simply because it's extraordinarily difficult to create such conditions in a laboratory. The boundary of our understanding becomes clear when considering that in Jupiter's deep interior, hydrogen itself, normally the lightest gas, is compressed into a metallic liquid state. If even the elements themselves undergo such dramatic phase changes, it's unreasonable to expect any conventional material to maintain its designed properties in such an environment. Electrical and electronic materials face additional challenges. Semiconductors, the foundation of modern electronics, rely on precisely controlled electron behavior. Under extreme pressures and temperatures, the carefully engineered properties of semiconductor materials change dramatically, causing electronic components to malfunction. Insulating materials become more conductive under pressure, potentially causing short circuits. Conductors experience changes in resistance that can lead to overheating and failure. Thermal management, critical for any spacecraft, becomes nearly impossible in Jupiter's deeper atmosphere. On Earth or in space, systems typically rely on radiating excess heat away or transferring it to a heat sink. In Jupiter's high-pressure, high-temperature environment, there's nowhere for the heat to go. The surrounding atmosphere is already hotter than the spacecraft. Any cooling system would require enormous energy to operate against this adverse thermal gradient, creating a spiral of increasing power requirements and heat generation. Material scientists continue to develop new substances that push the boundaries of what's possible. Metamaterials with engineered structures at the microscopic level, new metal alloys designed at the atomic scale, and carbon-based materials like graphene offer tantalizing possibilities. However, even these cutting-edge materials have fundamental physical limits. Chemical bonds can only withstand so much energy before breaking, and atomic structures can only be compressed so far before transforming into different states. The most promising materials for extreme environments often involve carbon-based structures. Diamond, the hardest naturally occurring substance, maintains its structure at higher pressures than almost any other material. Synthetic diamonds and similar carbon structures might withstand Jupiter's pressure better than alternatives, but even they would eventually reach their limits as depth increases. Additionally, diamond becomes vulnerable at high temperatures in the presence of oxygen it essentially burns. While Jupiter's hydrogen-helium atmosphere lacks significant oxygen, other reactive species present similar challenges. The reality is that no single material or combination of materials known to current science could withstand the full range of conditions found in Jupiter's deep atmosphere. Each class of materials fails under different aspects of Jupiter's hostile environment, but all would ultimately fail given sufficient depth. This fundamental material limitation is perhaps the most significant barrier to deep exploration of Jupiter with foreseeable technology. The material challenges of Jupiter directly impact another crucial aspect of planetary exploration: the ability to communicate with a probe as it descends into the atmosphere. Even if we could somehow design a spacecraft to survive deeper into Jupiter, we would face the equally daunting challenge of getting any data back from it. Communication through Jupiter's atmosphere presents unique obstacles that make maintaining contact with a descending probe increasingly difficult and eventually impossible. Radio waves are the standard medium for spacecraft communication, but Jupiter's atmosphere progressively attenuates these signals as depth increases. This attenuation occurs for several interconnected reasons, all becoming more severe with descent. The increasing density of the atmosphere absorbs and scatters radio signals, reducing their strength. A similar effect occurs in Earth's atmosphere during heavy rainstorms, but Jupiter's atmosphere becomes thousands of times denser than Earth's as depth increases. Beyond simple density effects, Jupiter's atmosphere contains significant concentrations of ammonia, which is particularly effective at absorbing microwave frequencies commonly used for spacecraft communication. This ammonia absorption creates radio dark regions in certain frequency bands, forcing communication systems to either use less affected frequencies or increase transmission power to compensate. As a probe descends deeper, the ionized particles in Jupiter's atmosphere create an additional communication challenge. Jupiter has intense radiation belts that extend into the upper atmosphere, creating regions with high concentrations of charged particles. These particles interact with electromagnetic waves, causing refraction, reflection, and absorption of radio signals. In some frequency bands, this can lead to almost complete signal blockage. The extreme pressure gradient in Jupiter's atmosphere causes radio waves to refract, bending their path as they travel through regions of different density. This refraction can prevent signals from following a direct path to receiving stations, requiring precise planning of communication windows and receiver positions. The Galileo mission addressed this by positioning the main spacecraft directly above the entry probe to maximize the chance of receiving transmissions through the atmosphere. Even with this optimal positioning, the Galileo probe's signal became progressively weaker as it descended. The mission was designed around this limitation. Data was transmitted continuously rather than stored for later transmission, ensuring that at least some information would be received before communications failed completely. When contact was lost after 58 minutes, it wasn't clear whether the probe itself had failed or simply could no longer transmit effectively through the thickening atmosphere. For a probe to transmit from significantly deeper in Jupiter's atmosphere, it would need exponentially more powerful radio equipment. The required power increases rapidly with depth, quickly exceeding what's practical for spacecraft power systems. Even with nuclear power sources like radioisotope thermoelectric generators, RTGs, the power requirements for deep transmission would eventually become prohibitive. One potential workaround would be a relay system, with multiple probes at different depths passing data up a chain to eventually reach a spacecraft in orbit. However, this approach multiplies the complexity and cost of a mission while still facing the fundamental physical limits of signal propagation through dense, conductive media. The communication challenge becomes even more complex due to Jupiter's rapid rotation. The planet completes a rotation in just under 10 hours, meaning that a probe's position relative to receiving stations changes quickly. Combined with the straight-line limitations of radio transmission through the atmosphere, this creates narrow communication windows that require precise timing. Alternative communication technologies face similar or worse limitations in Jupiter's environment. Optical communication using lasers, which offers higher data rates in space environments, would be blocked by cloud layers and atmospheric scattering even more readily than radio waves. Acoustic communication, sometimes used in Earth's oceans, would be limited by the dramatically different properties of Jupiter's atmosphere and the enormous distances involved. Even if a probe could somehow maintain its physical integrity in Jupiter's deep atmosphere, the inability to transmit data back would render the mission scientifically useless. A probe that can survive but not communicate becomes effectively blind to outside observers. This communication barrier represents a fundamental limitation that exists independently of material strength or thermal protection systems. The communication challenge also impacts mission design in less obvious ways. The uncertain communication environment means that probes must be highly autonomous, capable of making decisions without real-time input from Earth. This increases the complexity of onboard computing systems, which must themselves be hardened against Jupiter's radiation and other environmental factors. Data compression becomes critically important, allowing maximum scientific value to be extracted from limited bandwidth. The Galileo probe used sophisticated compression techniques to transmit as much atmospheric data as possible during its brief operational period. For deeper missions, even more aggressive compression would be necessary, potentially requiring artificial intelligence systems to identify and prioritize the most valuable data. Time delay compounds these challenges. Radio signals take 30 to 53 minutes to travel between Earth and Jupiter, depending on the planet's relative positions. This means that even for a probe in Jupiter's upper atmosphere, real-time control is impossible. Any mission must be largely pre-programmed or autonomous, with limited ability to adapt to unexpected conditions. The combination of atmospheric attenuation, ionospheric effects, power limitations, and time delay creates a communication barrier that becomes progressively more impenetrable with depth. Current technology allows communication through the outermost layers, as demonstrated by the Galileo mission, but deeper exploration would require fundamental breakthroughs in either communication technology or completely new approaches to planetary exploration. Until such advances occur, much of Jupiter's atmosphere will remain not only physically inaccessible but also communicationally silent to our attempts at exploration. The communication barriers represent just one of many compounding challenges that make Jupiter exploration so difficult. Even if we could somehow solve the problems of material limitations and signal transmission, any spacecraft would still need to contend with another fundamental force that's far more powerful on Jupiter than on Earth: gravity. Jupiter's enormous gravitational pull creates conditions that no current spacecraft could withstand for extended periods, particularly when combined with the planet's other environmental extremes. Jupiter is the most massive planet in our solar system, containing more than twice the mass of all other planets combined. This enormous mass generates a gravitational field approximately 2.5 times stronger than Earth's at the cloud tops, what scientists define as Jupiter's surface for measurement purposes. A human who weighs 180 pounds on Earth would experience the equivalent of 450 pounds of force on Jupiter, assuming they could find something solid to stand on. This increased gravitational strength presents multiple challenges for spacecraft design. Most obviously, it increases the structural loads on all components. A spacecraft structure engineered for Earth's gravity or the microgravity of space would experience significantly greater stresses in Jupiter's gravitational field. Components would effectively weigh more, pulling harder on their mounting points and support structures. Materials that are sufficiently strong for terrestrial or orbital missions could deform or break entirely under these increased loads. The stronger gravity also affects propulsion systems. Any spacecraft attempting to maneuver within Jupiter's atmosphere would require substantially more thrust to overcome the gravitational pull. This translates directly to increased fuel requirements, which means either carrying more propellant, adding to the spacecraft's mass and thus the gravitational force upon it, or accepting severely limited operational time within the atmosphere. For a probe descending into Jupiter, gravity creates a particularly vicious cycle. The greater gravitational pull accelerates the descent, which increases the atmospheric friction, generating more heat that the thermal protection system must handle. This faster descent also reduces the time available for scientific observations at each atmospheric layer. The Galileo probe experienced this accelerated descent, reaching deeper atmospheric layers more quickly than anticipated and limiting the data collection period. Jupiter's gravity doesn't just affect mechanical systems, it influences fluid systems as well. Propellant management becomes more challenging as gravity pulls liquids more strongly toward tank bottoms. Cooling systems that rely on fluid circulation face increased pumping requirements. Even the movement of gases within pressurized containers behaves differently under higher gravity, beyond the cloud tops. Jupiter's gravitational effect increases with depth as more of the planet's mass is concentrated beneath the spacecraft. This creates a gravitational gradient that subjects different parts of the spacecraft to slightly different forces, a phenomenon called tidal force. While these differential forces would be quite small for a typical spacecraft-sized object, they add another stress factor to systems already operating at their limits. The combination of strong gravity and rapid planetary rotation creates another effect that would challenge spacecraft systems: the varying centrifugal force across different latitudes. Jupiter completes a rotation in just under 10 hours despite its enormous size, generating significant centrifugal force that partially counteracts gravity, particularly at the equator. This creates a noticeable difference in effective gravity between polar and equatorial regions, about 7% less gravitational pull at the equator than at the poles. For a spacecraft attempting to operate for extended periods in Jupiter's atmosphere, this variation means that trajectory planning must account for these gravitational differences. A path that crosses multiple latitudes would experience changing gravitational forces, affecting everything from fuel consumption to sensor calibrations. The gravitational field also influences atmospheric dynamics in ways that complicate spacecraft operation. Jupiter's combination of strong gravity and rapid rotation helps drive its powerful jet streams and long-lived storm systems. These atmospheric features create regions where a spacecraft would experience additional forces beyond simple gravity: updrafts, downdrafts, and horizontal winds all impart accelerations that can exceed several times the base gravitational force. Perhaps most challenging from a mission design perspective is the fact that escaping Jupiter's gravity requires enormous energy. Once a spacecraft descends deeply into Jupiter's atmosphere, the energy required to climb back out becomes prohibitively large with current propulsion technology. This effectively means that atmospheric probes must be considered one-way missions, with no possibility of sample return or spacecraft recovery. The Juno spacecraft, currently in orbit around Jupiter, had to be carefully designed to cope with the planet's gravity. Its highly elliptical orbit was planned specifically to minimize time spent in the strongest regions of Jupiter's gravitational field, reducing the structural stresses on the spacecraft while still allowing close-up observations during brief periapsis passes. Even orbital mechanics around Jupiter present unique challenges due to the strong gravity. The planet's substantial gravitational reach means it significantly perturbs the orbits of nearby objects. This creates complex orbital stability issues that mission planners must account for, particularly for long-duration missions. Some orbits that would be stable around other planets become chaotic around Jupiter, potentially sending spacecraft into unplanned trajectories that could result in atmospheric entry and destruction. For human exploration, which remains firmly in the realm of science fiction for Jupiter, the gravity poses even greater challenges. The human body is not adapted to function under sustained forces greater than Earth's gravity. Extended exposure to Jupiter's gravitational force would likely cause cardiovascular problems, skeletal degradation, and muscle atrophy, even for astronauts in peak physical condition. These biological limitations place additional constraints on even theoretical human missions to Jupiter's vicinity. The gravitational challenge extends to scientific instruments as well. Many sensitive measurement devices are calibrated for specific gravitational conditions and may provide inaccurate readings when subjected to stronger fields. Mechanical components in instruments, such as pivots, gimbals, and scanning mirrors, require more robust motors and actuators to overcome the increased gravitational resistance. When combined with Jupiter's other environmental extremes, radiation, period, pressure, temperature, and chemical corrosion, the gravitational forces create a compounding effect. Each hazard alone presents significant challenges, but together they create an environment where solving one problem often makes another worse. Strengthening a structure to withstand gravity adds mass, which increases heat generation during entry. Adding thermal insulation increases volume, which increases atmospheric drag and structural loads. The gravity essentially amplifies the effects of every other environmental challenge, making the overall problem of Jupiter exploration exponentially more difficult than addressing any single factor. While Jupiter's gravity poses significant challenges to any spacecraft, it's the chaotic nature of the planet's atmospheric turbulence and the extreme shearing forces between atmospheric layers that would ultimately tear apart even the most robust spacecraft designed with current technology. These dynamic atmospheric forces represent some of the most immediately destructive aspects of Jupiter's environment. Jupiter's atmosphere doesn't move as a single unified body. Instead, it consists of numerous distinct layers and bands flowing at different speeds and directions. The boundaries between these regions, where fast-moving atmospheric streams flow alongside slower ones, create zones of intense shear that would subject a descending spacecraft to tremendous mechanical stress. The most visible manifestation of this layered structure is Jupiter's colourful banded appearance. The light-coloured zones and darker belts represent different atmospheric currents moving in opposite directions relative to each other. Where these bands meet, wind speeds can change by hundreds of kilometers per hour over vertical distances of just tens of kilometers, a wind gradient far more extreme than anything encountered in Earth's atmosphere. When a spacecraft crosses these boundary regions, it experiences rapidly changing aerodynamic forces from multiple directions simultaneously. Imagine the upper portion of a spacecraft being pulled strongly eastward while the lower portion is pushed westward. This creates a twisting force, or torque, that stresses the internal structure in ways difficult to design against. Unlike the relatively predictable stresses of launch or Earth atmospheric entry, these multidirectional forces come from all sides with patterns too complex to fully anticipate. The Galileo probe encountered this phenomenon during its descent. As it crossed boundaries between atmospheric bands, it experienced unexpected oscillations and rotations. While the probe was specifically designed to handle some degree of buffeting and had a spin-stabilized design to help maintain orientation, the atmospheric turbulence exceeded pre-mission estimates in many regions. The turbulence situation becomes significantly worse deeper in the atmosphere. In the upper cloud layers, flow tends to be predominantly horizontal in well-defined bands. Deeper down, three-dimensional circulation patterns develop, with powerful updrafts and downdrafts creating vertical shear in addition to horizontal differences. These vertical currents are particularly problematic for spacecraft, as they can suddenly accelerate a probe upward or downward, creating instantaneous g-forces many times the background Jovian gravity. Jupiter's atmospheric dynamics operate on scales both vastly larger and more intense than Earth's weather systems. The largest storm features, like the Great Red Spot, contain wind patterns that would encompass entire countries on Earth. Even small turbulent eddies in Jupiter's atmosphere can be hundreds of kilometers across, large enough to engulf an entire spacecraft and subject it to chaotic, swirling forces from all directions. The turbulence spectrum in Jupiter's atmosphere extends from these massive features down to microscopic scales. This creates a cascade of vortices and eddies of decreasing size but increasing frequency. A spacecraft would experience not just large-scale buffeting, but also high-frequency vibrations that could excite structural resonances, potentially causing catastrophic failure even in components designed to withstand the larger forces. Computational fluid dynamics models suggest that in certain regions of Jupiter's atmosphere, particularly in and around storm systems, turbulence intensities could reach levels several orders of magnitude greater than the most severe clear air turbulence encountered by aircraft on Earth. Under such conditions, even modest-sized spacecraft would experience random acceleration spikes equivalent to several times Jupiter's already substantial gravity. The chaotic nature of this turbulence makes it particularly difficult to design against. Engineering typically relies on understanding the maximum forces a structure will experience and then designing with an appropriate safety margin. Jupiter's atmospheric turbulence creates a situation where the peak forces are difficult to predict and can come from any direction at any time. This unpredictability necessitates either extremely conservative design with massive structural reinforcement adding weight that creates other problems or acceptance of higher mission risk. The shearing problem becomes even more severe around Jupiter's distinct atmospheric features. The Great Red Spot, for example, has persisted for centuries precisely because it exists in a state of dynamic equilibrium with its surroundings, continuously drawing energy from the shear between different atmospheric currents. These same forces that sustain the storm would work to tear apart any spacecraft attempting to traverse its boundaries. Around the periphery of the Great Red Spot, wind speeds change from approximately 100 km per hour in surrounding regions to over 400 km per hour within the storm, all within a transition zone just tens of kilometers wide. This creates a shear gradient that would subject a spacecraft to forces similar to being grabbed on opposite ends and twisted violently in opposite directions. Similar but less famous features exist throughout Jupiter's atmosphere. The white ovals, brown barges, folded filamentary regions, and numerous smaller vortices all create localized regions of intense shear and turbulence. A spacecraft's path through the atmosphere would inevitably cross numerous such features, each presenting its own unique pattern of destructive forces. The material challenges discussed earlier compound the turbulence problem. Materials become more brittle under extreme cold, more plastic under extreme heat, and generally less resilient under both conditions. The temperature gradient in Jupiter's atmosphere means that different parts of a spacecraft would be at different temperatures, responding differently to the same mechanical stresses. A structure that might survive turbulence in uniform conditions would be much more vulnerable when some components are at negative 100 degrees Celsius while others have heated to positive 150 degrees Celsius. The atmospheric shearing also interacts with the planet's electromagnetic environment in ways that create additional hazards. The rapid movement of conductive atmospheric gases through Jupiter's powerful magnetic field generates electric currents and localized magnetic anomalies. These, in turn, can induce currents in spacecraft components, potentially causing electrical interference, heating, or even component failure during periods of intense atmospheric turbulence. Even with advances in materials science and structural design, the fundamental challenge of Jupiter's atmospheric shear and turbulence remains a nearly insurmountable obstacle with current technology. A spacecraft capable of withstanding these forces would need to be either impractically massive and reinforced or designed with extraordinary flexibility to absorb and dissipate the chaotic forces. Either approach creates cascading engineering challenges that push well beyond current capabilities, especially when combined with Jupiter's many other environmental extremes. Even with a hypothetical spacecraft design that could somehow withstand Jupiter's atmospheric turbulence and shearing forces, we would immediately face another fundamental challenge: how to power such a mission. The energy requirements for operating in Jupiter's hostile environment far exceed what current spacecraft power systems can provide, creating yet another barrier to deeper exploration of the gas giant. Spacecraft require electrical power for nearly every aspect of their operation, from running scientific instruments and transmitting data to maintaining thermal control and operating navigation systems. On missions to the outer solar system, including Jupiter, power generation presents unique challenges that become even more severe when attempting to operate within the planet's atmosphere. The most common power source for Earth-orbiting satellites, solar panels, becomes increasingly impractical as spacecraft venture farther from the Sun. At Jupiter's distance, solar energy is only about 4% as intense as at Earth. This significant reduction means that a spacecraft would need solar arrays roughly 25 times larger to generate the same power as an Earth-orbiting satellite. Such enormous solar panels would create insurmountable drag in Jupiter's atmosphere, quickly destroying the spacecraft or sending it into an uncontrolled tumble. Moreover, solar power becomes completely useless once a probe descends below Jupiter's cloud tops. The thick, ammonia-rich clouds block virtually all sunlight. creating conditions of near-total darkness in the deeper atmosphere. The Galileo probe experienced this transition, with light levels dropping precipitously as it penetrated below the uppermost cloud layers. Any probe designed to explore Jupiter's depths would need to rely entirely on onboard power sources without any solar contribution. The standard alternative for deep space missions has traditionally been radioisotope thermoelectric generators, RTGs, which convert heat from radioactive decay into electricity. The Galileo orbiter used this technology, as have other outer planet missions like Cassini, New Horizons, and the Voyager probes. However, RTGs produce relatively modest amounts of power. The RTGs on the Cassini spacecraft generated less than 1,000 watts at the beginning of its mission, comparable to a small household microwave oven. This power level is sufficient for operating scientific instruments on an orbiter but falls far short of what would be needed for a probe attempting to survive in Jupiter's atmosphere. The energy required to maintain thermal control alone would exceed the output of typical RTG systems as the external temperature rises from the frigid upper atmosphere to the increasingly hot lower regions. Active cooling systems, necessary to protect electronics from Jupiter's heat, would consume enormous amounts of power. Communication represents another major power challenge. Transmitting data through Jupiter's thick atmosphere would require significantly more powerful radio systems than those used for vacuum transmission. As a probe descends and atmospheric density increases, the power needed to maintain communication grows exponentially. The Galileo probe addressed this by using a relatively low data rate and positioning the main orbiter directly overhead during descent. But even so, communications failed after less than an hour. An additional power-hungry system would be any propulsion or attitude control mechanisms. While the Galileo probe was designed to simply fall through Jupiter's atmosphere without active control, any mission attempting to maneuver or maintain position within specific atmospheric layers would need substantial propulsive capability. The energy required for such maneuvers increases with atmospheric density and would quickly exceed the capacity of current spacecraft power systems. Nuclear fission reactors represent a potentially more powerful alternative to RTGs. Space-based nuclear reactors can generate tens or even hundreds of kilowatts of power, potentially providing enough energy for more capable Jupiter atmospheric probes. However, these systems come with significant downsides, including increased mass, complexity, and safety concerns. No nuclear reactor has flown in space on a U-dot mission since the SNAP-10A in 1965, though Russia has launched several spacecraft with nuclear reactors. Even with nuclear power, the thermal management challenges in Jupiter's atmosphere would be enormous. Nuclear reactors generate substantial waste heat that must be dissipated, typically through radiators that release the heat into space. In Jupiter's dense atmosphere, these radiators would become ineffective as the external temperature rises, potentially causing the reactor to overheat and shut down. Battery technology, while advancing rapidly, remains insufficient for extended operations in Jupiter's atmosphere. The most advanced lithium-ion batteries have energy densities approximately 200 watt-hours per kilogram, enough to power a probe for hours, perhaps, but not for the extended periods needed for significant scientific exploration. Moreover, battery performance degrades significantly under both the extreme cold of Jupiter's upper atmosphere and the high temperatures found deeper down. Fuel cells, which generate electricity through chemical reactions, offer higher energy density than batteries but require reactants like hydrogen and oxygen that add mass and complexity to the spacecraft. They also produce water as a byproduct, which would freeze in the upper atmosphere or create pressure management challenges deeper down. Any combination of these power systems would face the additional challenge of Jupiter's intense radiation environment, which degrades solar cells, affects electronics in power management systems, and can even impact the performance of RTGs by damaging their thermoelectric materials. Radiation-hardened power systems add further mass, complexity, and cost to an already challenging mission design. The energy situation creates a particularly frustrating catch-22 for Jupiter exploration. More capable power systems typically require larger, heavier components, but larger spacecraft face greater challenges from Jupiter's atmospheric forces. Conversely, smaller, more streamlined probes would experience less atmospheric stress but have severely limited power availability for systems and instruments. The Galileo probe addressed these challenges through extreme minimalism. It carried just enough battery power for its brief mission and a focused instrument payload designed for maximum science return during its short operational period. Even so, it only scratched the surface of Jupiter's atmospheric structure. A probe designed to penetrate significantly deeper would require a revolutionary approach to spacecraft power generation and management. Innovative concepts like wireless power transmission from an orbiter to an atmospheric probe have been proposed but remain technologically immature for the distances and atmospheric conditions involved. Without a major breakthrough in compact, high-density power generation, the energy requirements of operating in Jupiter's hostile environment will continue to severely limit our ability to explore beyond the planet's outermost atmospheric layers. As a spacecraft would descend deeper into Jupiter's atmosphere, facing all these compounding challenges of pressure, temperature, turbulence, and energy limitations, it would eventually encounter one of the most exotic environments in our solar system, a layer of hydrogen that behaves not like a gas, but like a metal. This phenomenon, known as metallic hydrogen, represents perhaps the most alien and inaccessible region of Jupiter's structure. Metallic hydrogen forms under conditions of extreme pressure and temperature not naturally found on Earth. In Jupiter's interior, at approximately 20,000 kilometers below the visible cloud tops, the pressure reaches millions of times Earth's atmospheric pressure while temperatures soar to thousands of degrees Celsius. Under these extraordinary conditions, hydrogen undergoes a phase transition fundamentally different from the familiar changes between solid, liquid, and gas that we observe in everyday life. In normal hydrogen gas, each hydrogen atom bonds with another to form molecular hydrogen H2. The electrons in these molecules are tightly bound to their respective atoms, making the gas an electrical insulator. However, as pressure increases dramatically, these hydrogen molecules are forced so close together that the distinction between individual molecules begins to break down. At a certain threshold, the electrons are no longer bound to specific atoms, but become free to move throughout the material, the defining characteristic of a metal. This transition creates a substance with extraordinary properties. Metallic hydrogen conducts electricity like copper or silver, despite being formed from what's normally an insulating gas. It's also believed to be highly reflective, potentially with the appearance of a shiny metal. Yet, unlike familiar metals that are solids at room temperature, Jupiter's metallic hydrogen exists as a fluid, a liquid metal made from the most abundant element in the universe. The metallic hydrogen layer is crucial to understanding Jupiter's most distinctive features. This electrically conductive region, combined with Jupiter's rapid rotation, generates the planet's enormous magnetic field, the strongest in the solar system apart from the Sun itself. As this fluid metallic hydrogen moves within Jupiter's interior, it creates electrical currents on a massive scale that sustain and shape the magnetosphere extending millions of kilometers into space. For any spacecraft that could theoretically reach this depth, a technological feat far beyond current capabilities, the metallic hydrogen region would present uniquely destructive conditions. Beyond the already lethal pressure and temperature, the environment would be fundamentally incompatible with normal electronic operations. The electrically conductive nature of metallic hydrogen would create a situation where the spacecraft would be surrounded by what amounts to a highly conductive fluid. Any attempt to operate electrical systems would result in immediate short-circuiting, as current would flow through the surrounding medium rather than through intended pathways in the spacecraft's systems. Standard electrical insulation would fail, not just because of the extreme conditions, but because of the fundamentally different electrical environment. The fluid metallic hydrogen would also conduct heat extremely efficiently, making thermal management essentially impossible. Any temperature difference between the spacecraft and its surroundings would equilibrate nearly instantly, overwhelming any conventional cooling system. Electronics require operating within specific temperature ranges, but maintaining any temperature differential in such an environment would be thermodynamically unfeasible with current technology. Metallic hydrogen also interacts strongly with magnetic fields, including any generated by spacecraft components, electric motors, solenoids, or any magnetically actuated devices would experience severe interference. The surrounding medium would create induced currents that oppose the intended operation of such devices, potentially rendering them inoperable or causing them to behave in unpredictable ways. Perhaps most alien from a materials perspective is how metallic hydrogen would interact with the spacecraft's structural materials. Hydrogen in its metallic state can potentially infiltrate other materials at the atomic level, causing hydrogen embrittlement far more severe than what occurs in normal hydrogen environments. Metals that might briefly withstand the pressure and temperature could rapidly become brittle and fail due to hydrogen infiltration. The boundary between normal molecular hydrogen and the metallic phase isn't sharply defined. As a spacecraft would descend, it would encounter a transition region where hydrogen gradually develops metallic properties. This creates an additional challenge. Systems might begin failing in subtle, unpredictable ways before reaching the fully metallic region. Partial conductivity might cause intermittent electrical issues or gradual degradation rather than immediate failure, potentially creating confusing diagnostic scenarios if telemetry could somehow be maintained. Scientists believe that above the metallic hydrogen layer, Jupiter may contain a region where hydrogen exists in an unusual intermediate state, a supercritical fluid with partially ionized properties. This transition zone would itself present unique challenges distinct from either the gaseous upper atmosphere or the fully metallic deeper regions. Engineering for such exotic states of matter goes well beyond current materials science and spacecraft design capabilities. One particularly fascinating aspect of the metallic hydrogen region is that it's believed to be in constant motion, with complex flow patterns driven by Jupiter's internal heat and rotation. These flows would create turbulent conditions even more extreme than those in the gaseous atmosphere above. Any spacecraft would not only face the chemical and electrical hostility of the environment, but would also be subjected to powerful, chaotic mechanical forces from the flowing metallic hydrogen. The closest laboratory analogue we have to Jupiter's metallic hydrogen comes from high-pressure physics experiments using diamond anvil cells, where tiny samples of hydrogen are compressed between diamond tips to pressures of hundreds of gigapascals. Even in these experiments, achieving true metallic hydrogen remains at the frontier of current scientific capabilities, and the samples created are microscopic and exist only briefly, creating materials that could function in this environment, or even studying how conventional materials behave under such conditions, stretches beyond current experimental capabilities. The metallic hydrogen layer essentially forms a boundary beyond which exploration with foreseeable technology becomes not just extremely difficult but fundamentally impossible based on our current understanding of materials and physics. While we can remotely study this region through its effects on Jupiter's observable properties like the magnetic field, direct exploration would require technological approaches so advanced they would appear, as Arthur C. Clarke famously noted, indistinguishable from magic to contemporary engineers and scientists. While Jupiter's metallic hydrogen region represents perhaps the most extreme environment in our solar system, it's worth considering how Jupiter compares to the other gas giants. Although all the giant planets present formidable challenges to exploration, each has unique characteristics that make them hostile to spacecraft in different ways. Understanding these similarities and differences helps clarify why Jupiter stands out as particularly inaccessible. Saturn, the second largest planet in our solar system, shares many characteristics with Jupiter, but presents a somewhat less extreme environment in several key aspects. Like Jupiter, Saturn is composed primarily of hydrogen and helium, with a similar overall structure including a metallic hydrogen layer and a molecular hydrogen atmosphere. However, Saturn's smaller mass, about 95 Earth masses compared to Jupiter's 318, results in lower internal pressures and temperatures. The lower gravitational pull at Saturn's cloud tops, about 90% of Earth's gravity compared to Jupiter's 2.5 times Earth's, would subject a spacecraft to less structural stress. Saturn's magnetic field, while still powerful, is only about 20 times stronger than Earth's, compared to Jupiter's field that's 14 times stronger than Earth's. This creates a less intense radiation environment, with radiation belts that would damage spacecraft more slowly than Jupiter's. Saturn's winds are actually faster than Jupiter's in some regions, reaching speeds of 1,800 kilometers per hour near the equator, about 3 times faster than Jupiter's fastest jets. However, the lower atmospheric density means these winds exert less force on objects moving through them. The vertical wind shear between atmospheric layers also appears less extreme than on Jupiter, potentially subjecting spacecraft to less mechanical stress during descent. Temperature gradients in Saturn follow a similar pattern to Jupiter, with frigid cloud tops warming to extreme temperatures in the interior, but the absolute temperatures are generally lower throughout. Saturn's cloud top temperature is approximately negative 178 degrees Celsius, even colder than Jupiter's, creating additional challenges for spacecraft operating in the upper atmosphere. Perhaps the most distinctive feature affecting Saturn exploration is its famous ring system. While beautiful from a distance, the rings present a hazardous region for spacecraft, with countless particles ranging from microscopic dust to boulder-sized objects orbiting at high velocities. Any mission to the Saturnian system must carefully navigate to avoid ring crossings at dangerous velocities or locations. The Cassini mission, which explored the Saturn system from 2004 to 2017, revealed much about the challenges of operating near a gas giant. Despite Saturn's somewhat less extreme environment compared to Jupiter, Cassini still required careful trajectory planning to manage radiation exposure and ring hazards. The mission ended with a deliberate plunge into Saturn's atmosphere, where the spacecraft was destroyed within minutes due to atmospheric forces, despite entering at a shallow angle to extend its transmission time. Moving outward to Uranus and Neptune, we find ice giants rather than gas giants, a crucial distinction in composition that affects their internal structure. Unlike Jupiter and Saturn, which are predominantly hydrogen and helium, Uranus and Neptune contain significant amounts of ices such as water, ammonia, and methane in their interiors. These substances create different layering within the planets and different challenges for potential exploration. One might initially think these smaller, more distant worlds would be less hostile to spacecraft than Jupiter, but they present their own extreme conditions. Uranus has the coldest measured atmospheric temperature of any planet in our solar system, reaching as low as negative 224 degrees Celsius. This extreme cold creates materials challenges opposite to the heat problems on Jupiter, potentially making materials brittle and causing electronic components to fail. Neptune features the strongest winds in the solar system, with speeds recorded up to 2,100 kilometers per hour. Despite its smaller size and lower gravity than Jupiter, these winds would create severe mechanical stresses on any atmospheric probe. Both ice giants have substantial magnetic fields, though oriented unusually compared to other planets, creating complex radiation environments that would affect spacecraft electronics. Perhaps the most significant difference affecting exploration is the pressure-temperature profile. In Jupiter, pressure and temperature increase rapidly with depth. On Uranus and Neptune, the transition from the hydrogen-helium atmosphere to the water-ammonia-methane mantle occurs at lower pressures, creating a potentially more accessible boundary region. However, This boundary would still lie far below the crushing pressures survivable by current spacecraft technology. A common feature across all giant planets that makes them particularly challenging is their lack of a solid surface. On Mars, or even Venus, a spacecraft can be designed to reach a definitive endpoint, the planetary surface, and operate there. On the giants, a probe must be designed for a continuous descent through progressively more extreme conditions, with no stable surface to target for landing. The distance from Earth also significantly affects exploration difficulty. Jupiter, while extremely challenging to explore, is at least relatively close, with one-way light time ranging from 33 to 53 minutes depending on orbital positions. Neptune, in contrast, is so distant that radio signals take over 4 hours to reach Earth, making real-time intervention impossible and requiring spacecraft to be fully autonomous in handling emergencies. When considering the total hostility to spacecraft, Jupiter maintains its position as the most challenging overall due to the combination of extreme radiation, powerful gravity, intense pressure gradient, and severe temperature range. While each giant planet presents unique challenges, none combines as many severe hazards in one environment as Jupiter does. This helps explain why, despite multiple missions to Jupiter, we've only managed the briefest of atmospheric penetrations with the Galileo probe, while the deeper regions remain completely inaccessible with current technology. Given the extreme conditions that make direct exploration of Jupiter's depths impossible with current technology, scientists and engineers have proposed alternative approaches that might allow longer duration studies of the giant planet's atmosphere. The most promising of these concepts involves aerostatic aircraft, essentially period, balloons or similar floating platforms that could remain suspended in specific atmospheric layers without needing to fight against crushing pressures below or escape back to space above. The basic principle behind aerostatic exploration is straightforward. A balloon filled with a gas lighter than the surrounding atmosphere will float at an altitude where its average density equals that of the ambient atmosphere. On Jupiter, this creates interesting possibilities because the primary atmospheric component is hydrogen, the lightest gas known. This presents a fundamental challenge. What gas could possibly be used to create buoyancy in an atmosphere already made of the lightest element? The solution comes from temperature differences rather than gas composition. A heated volume of hydrogen gas is less dense than the same volume of colder hydrogen. By creating what's called a hot air balloon design, but using hot hydrogen instead of hot air, a properly designed craft could theoretically achieve buoyancy even in Jupiter's hydrogen-dominated atmosphere. Alternatively, the extreme cold of Jupiter's upper atmosphere actually causes hydrogen to be quite dense compared to the same gas at warmer temperatures. A balloon containing hydrogen maintained at a higher temperature than the surrounding atmosphere could generate sufficient lift to support a scientific payload. The temperature differential wouldn't need to be enormous. Even a difference of 50 to 100 degrees could provide adequate buoyancy. This approach would allow a floating platform to establish equilibrium at a particular atmospheric layer, potentially maintaining that position for weeks or even months. By adjusting the temperature of the lifting gas, the craft could potentially rise or descend to sample different atmospheric levels, though the range would be limited to regions with survivable conditions. The ideal operating zone for such a floating platform would be in Jupiter's upper troposphere, below the cloud tops but above the regions where pressure and temperature become extreme. This zone, extending perhaps 100 to 300 kilometers below the visible cloud tops, represents a region where meaningful scientific observations could be conducted while conditions remain just within the operating limits of specially designed instruments. Several advantages make this approach attractive. A floating platform doesn't need to expend energy continuously fighting gravity or atmospheric pressure. Once at equilibrium, it requires minimal power to maintain altitude, allowing limited energy resources to be dedicated primarily to scientific instruments and communications. The platform would also move with the surrounding atmospheric currents, reducing the relative wind speed to near zero and minimizing aerodynamic stresses on the structure. NASA and other space agencies have studied various concepts for Jupiter atmospheric explorers using this principle. One design, called the Jupiter Atmospheric Floater, JAF, envisions a probe with a diameter of about 4 meters, carrying approximately 25 kilograms of scientific instruments. The floating duration could potentially extend to 30 to 90 days, compared to the less than 1 hour achieved by the Galileo descent probe. Another concept, more ambitious in scope, proposes a larger platform called the Jupiter Atmospheric Science Platform JASP, with enhanced capabilities for atmospheric sampling, weather monitoring, and potentially even deploying small sub-probes to briefly sample conditions below the main floating altitude. Such a platform might operate for 6 months or longer, providing unprecedented long-term observations of Jupiter's atmospheric dynamics. The engineering challenges, while still formidable, become somewhat more manageable with the floating approach. The craft would need to withstand the cold temperatures of Jupiter's upper atmosphere, radiation effects, and chemical corrosion, but would avoid the most extreme pressure and temperature conditions found deeper down. Power could be provided by advanced radioisotope thermoelectric generators, RTGs, similar to those used on current outer planets missions, potentially supplemented by fuel cells for peak power demands. The balloon material itself presents a significant technical challenge. It would need to be lightweight, yet strong enough to withstand the turbulence of Jupiter's atmosphere. It would also need to be resistant to chemical degradation from ammonia, hydrogen sulfide, and other reactive compounds present in the atmosphere. Advanced materials like polybenzooxazole fibers or metallic microlattices might provide the necessary combination of strength, flexibility, and chemical resistance. Communication remains a critical design driver. A floating platform in Jupiter's atmosphere would still face significant challenges in transmitting data back to Earth. One approach would be to include a relay satellite in Jupiter orbit that could receive transmissions from the floating platform and relay them to Earth using a more powerful transmitter and larger antenna than could be accommodated on the platform itself. Thermal management would require careful engineering. The same temperature difference used to create buoyancy would tend to equilibrate over time through heat transfer with the surrounding atmosphere. The platform would need systems to generate heat continuously to maintain its lifting capability. This heat generation would need to be precisely controlled to maintain the desired altitude without wasting limited energy resources. Navigation and position determination would rely primarily on tracking atmospheric features and potentially star sightings during brief clear periods, as GPS-like systems don't exist at Jupiter. The craft would essentially drift with Jupiter's winds, potentially traversing significant portions of the planet during an extended mission and sampling different latitudinal regions. While technologically challenging, the floating platform approach represents perhaps the most viable near-term solution for extended exploration of Jupiter's atmosphere. It avoids the need to solve the impossible problems of surviving in the deep atmosphere while still allowing meaningful scientific return from regions inaccessible to remote sensing from orbit. The concept has grown more feasible in recent years as materials science has advanced and as we've gained experience with similar technologies. NASA's successful deployment of the Ingenuity helicopter on Mars demonstrated our growing capability with aerial vehicles on other worlds, while various high-altitude balloon missions on Earth have tested technologies applicable to extreme environment exploration. The European Space Agency's proposed Venus atmospheric balloon similarly addresses many of the same engineering challenges that would apply to a Jupiter mission. While still beyond our immediate technological reach, floating atmospheric platforms represent the most promising approach for future in-situ exploration of Jupiter's atmosphere, potentially opening a window into a world that remains largely inaccessible to conventional spacecraft designs. While floating platforms represent promising technology for future exploration, nature has already provided us with unintentional probes of Jupiter's atmosphere in the form of comets and asteroids that have collided with the giant planet. These natural impact events offer valuable insights into Jupiter's atmospheric behavior and destructive potential, with the most famous example being the collision of comet Shoemaker-Levy 9 with Jupiter in July 1994. Shoemaker-Levy 9 was an extraordinary event in astronomical history, the first collision of two solar system bodies ever observed in real time. The comet had been captured by Jupiter's gravity and broken apart into 21 distinct fragments during a close approach in 1992. 2 years later, these fragments, some measuring up to 2 kilometers in diameter, slammed into Jupiter's southern hemisphere over the course of 6 days. The impacts created enormous fireballs that rose up to 3,000 kilometers above Jupiter's cloud tops, higher than the diameter of Earth. Dark scars appeared in Jupiter's atmosphere where the fragments hit, with some impact sites larger than Earth in diameter. These scars remained visible for many months, gradually dispersed by Jupiter's winds and atmospheric circulation. What makes the Shoemaker-Levy 9 impact particularly relevant to our discussion of spacecraft survival is the fate of the comet fragments themselves. Despite being composed of rock and ice many times more durable than any human-made spacecraft, these massive objects were completely destroyed within minutes of entering Jupiter's atmosphere. The largest fragments penetrated perhaps 100 to 200 kilometers before being vaporized by a combination of atmospheric friction, pressure, and the resulting shock waves. The Galileo spacecraft, en route to Jupiter during the impacts, had a direct view of the collisions and recorded thermal flashes consistent with temperatures reaching tens of thousands of degrees Celsius as the comet fragments were destroyed. These temperatures far exceed what any known material could withstand, confirming the insurmountable thermal challenges faced by potential probes. The impact also provided insights into Jupiter's atmospheric structure. As the comet fragments disintegrated, they created massive plumes that briefly exposed deeper atmospheric layers not normally visible to observers. Spectroscopic analysis of these plumes revealed the presence of compounds from layers normally hidden beneath the visible clouds, effectively providing a natural form of atmospheric sampling. The behavior of the impact debris also demonstrated the complex fluid dynamics of Jupiter's atmosphere. The dark scars from the impacts were gradually shaped by Jupiter's differential rotation and wind patterns, with material in different latitude bands being stretched in different directions. This natural experiment revealed details about atmospheric circulation that would be difficult to measure even with dedicated probes. Since Shoemaker-Levy 9, astronomers have observed several additional impact events on Jupiter. In July 2009, an amateur astronomer in Australia noticed a dark spot near Jupiter's south pole that hadn't been there the night before. Analysis confirmed this was the result of an asteroid or comet roughly 500 to 1,000 meters in diameter striking the planet. Similar impacts were observed in June 2010, August 2012, March 2016, and May 2018, among others. The frequency of these observed impacts, roughly one detectable event every 1 to 3 years, suggests that Jupiter experiences substantial collisions much more regularly than previously thought. Each of these natural impactors serves as an unintentional probe, momentarily disturbing the atmosphere and revealing information about its composition and behavior. These impacts also illustrate Jupiter's role as a sort of cosmic shield for the inner solar system. Its enormous gravitational field attracts many objects that might otherwise continue toward the inner planets, potentially including Earth. The frequency of impacts observed on Jupiter suggests that without this protective effect, Earth would face a substantially higher impact threat from comets and asteroids. From a materials perspective, natural impacts provide sobering evidence of Jupiter's destructive potential. Even objects composed of solid rock and ice, materials far more durable than the metals, ceramics, and composites used in spacecraft construction are completely obliterated within minutes of atmospheric entry. The most robust natural materials in our solar system cannot survive Jupiter's atmospheric conditions for more than the briefest periods. The energies involved in these natural impacts are staggering. The Shoemaker-Levy 9 fragments each released energy equivalent to hundreds of thousands of megatons of TNT, many times the world's entire nuclear arsenal. Yet even these enormous energies were quickly absorbed and dissipated by Jupiter's vast atmosphere, demonstrating its incredible capacity to destroy anything entering it. Observed impacts have all occurred in Jupiter's upper atmosphere, but they provide indirect information about deeper regions as well. The way impact debris spreads and evolves over time gives clues about wind patterns and atmospheric stability at various depths. The chemical signatures detected in impact plumes reveal compounds dredged up from lower atmospheric layers, offering glimpses of regions we cannot directly observe. Perhaps most relevant to spacecraft design, natural impacts demonstrate the sheer scale disparity between human technology and Jupiter's environment. When objects kilometers in diameter, thousands of times larger than any conceivable spacecraft, are destroyed almost instantly. It puts into perspective the challenges facing any human-made probe attempting to penetrate beyond the most superficial atmospheric layers. These natural experiments continue to provide valuable data with each new impact observed. Modern telescopes with advanced adaptive optics can now resolve details of impact sites and track their evolution with unprecedented clarity. The James Webb Space Telescope, with its enhanced infrared capabilities, promises even more detailed observations of future impacts, potentially revealing new insights into Jupiter's atmospheric chemistry and dynamics. While natural impacts can't replace purpose-built scientific probes, they offer complementary information that helps build our overall understanding of Jupiter's hostile environment. Each collision serves as a reminder of the extraordinary forces at work in Jupiter's atmosphere, forces that continue to place significant portions of the giant planet beyond our technological reach. Looking to the future of Jupiter exploration, we find ourselves at a fascinating crossroads of technological capability and scientific ambition. Despite all the challenges we've discussed, our drive to understand this enormous world continues to inspire new mission concepts and technological approaches that may eventually allow us to probe deeper into its mysteries. Near-term exploration of Jupiter will likely focus on orbital missions similar to NASA's Juno spacecraft, which has been studying Jupiter since July 2016. Juno's unique polar orbit allows it to minimize exposure to the most intense radiation belts while still making close approaches that provide detailed measurements of Jupiter's gravity field, magnetic environment, and atmospheric composition. This approach, observing from above rather than directly entering the most hostile regions, represents our most viable strategy with current technology. The European Space Agency's Jupiter Icy Moons Explorer, JUICE, scheduled for launch in April 2023, will further expand our understanding of the Jupiter system, though it will focus primarily on the planet's moons rather than Jupiter itself. NASA's Europa Clipper mission, planned for launch in October 2024, similarly prioritizes exploration of Jupiter's moon Europa, but will still provide valuable context about Jupiter's overall environment. For direct atmospheric exploration, short-duration probes similar to the Galileo entry probe remain the most feasible approach in the near term. Future atmospheric probes would likely be designed to operate for longer periods than Galileo's 58 minutes, but would still be limited to the upper atmospheric layers. Improved materials, more radiation-hardened electronics, and more efficient power systems could potentially extend operational lifetimes to several hours, allowing deeper penetration but still falling far short of reaching Jupiter's deeper regions. The floating platform concepts discussed earlier represent perhaps the most promising medium-term approach for extended in-situ exploration. A Jupiter balloon mission has been proposed several times in NASA mission selection competitions, but has not yet been selected for development. As balloon technology advances through programs like NASA's Venus exploration initiatives, the technological readiness for Jupiter applications increases as well. More speculative concepts involve networks of small, distributed probes rather than single large spacecraft. Dozens or even hundreds of miniaturized probes could be deployed to sample different regions of Jupiter's atmosphere simultaneously, each transmitting data for as long as possible before succumbing to the environment. While each individual probe might survive only briefly, the collective dataset could provide unprecedented spatial coverage of Jupiter's atmospheric conditions. Some researchers have proposed sacrificial probe chains, where a series of increasingly robust probes would be released sequentially, each designed to operate slightly deeper than the last. Each probe would relay data to the one above it before being destroyed, creating a communication chain that could potentially reach unprecedented depths. While expensive and complex, such an approach could incrementally extend our exploration range. Advances in materials science offers some hope for more capable Jupiter probes. Diamond-based semiconductors, which can operate at much higher temperatures than silicon, might extend the thermal range of probe electronics. Carbon nanotube and graphene-based structural materials might provide better strength-to-weight ratios for withstanding Jupiter's atmospheric forces. Aerogels and other advanced insulating materials could offer improved thermal protection with less mass penalty. Power systems remain a critical limitation, but alternatives to traditional RTGs are under development. More efficient thermoelectric materials could increase power output from radioisotope systems. Small fission reactors, like NASA's Kilopower project, could potentially provide the higher power levels needed for more capable atmospheric probes, though significant engineering challenges remain in adapting such systems to the Jovian environment. Communication technologies are also advancing in ways that might benefit Jupiter exploration. Optical communication systems, which use lasers rather than radio waves, offer higher data rates with lower power requirements and smaller hardware. While Jupiter's clouds would block optical transmissions from deep probes, relay satellites in orbit could potentially receive optical signals from atmospheric probes and retransmit them to Earth via more powerful radio systems. Computational advances may also play a key role in future exploration. Artificial intelligence systems could allow probes to autonomously adapt to changing conditions, prioritize scientific observations based on discoveries, and manage limited resources to extend mission lifetime. Edge computing architectures could process raw data on board, transmitting only the most scientifically valuable information and thus making more efficient use of limited communication bandwidth. Despite these promising developments, we must acknowledge that certain regions of Jupiter will likely remain inaccessible to direct exploration for the foreseeable future. The metallic hydrogen layer and anything below it present fundamental physical challenges that go beyond incremental improvements in current technologies. Exploring these regions would require revolutionary approaches that might include entirely new propulsion concepts, exotic materials not yet invented, or radical rethinking of the very concept of a spacecraft. For the deepest regions, indirect exploration will remain our primary tool. Advanced computer models incorporating data from orbiters, atmospheric probes, and astronomical observations can simulate conditions in Jupiter's interior with increasing accuracy. Seismological techniques similar to those used to study Earth's interior might eventually be applied to Jupiter, using the planet's natural oscillations to infer properties of its deepest layers. Laboratory experiments can also advance our understanding without direct exploration. High-pressure physics experiments continue to push the boundaries of what's possible in recreating Jupiter-like conditions on Earth. While we can't match the scale of Jupiter's environment, we can study the behavior of materials under increasingly extreme conditions, informing our models of the planet's interior. In the longer term, the most transformative technologies for Jupiter exploration might come from fields not traditionally associated with space exploration. Advances in quantum computing could enable simulations of Jupiter's interior with unprecedented accuracy. Synthetic biology might eventually offer biological sensing systems capable of operating in environments where electronics fail. Molecular manufacturing could potentially enable new classes of materials with properties specifically engineered for the Jovian environment. While many of these approaches remain speculative, the history of space exploration has consistently demonstrated humanity's ingenuity in overcoming seemingly insurmountable challenges. The same creative problem-solving that allowed us to reach the Moon, land rovers on Mars, and send spacecraft beyond our solar system will continue to push the boundaries of what's possible in Jupiter exploration. Though much of Jupiter may remain physically inaccessible to our spacecraft, our understanding of this magnificent world will continue to deepen through a combination of direct observation, remote sensing, computer modelling, and laboratory experimentation, gradually unveiling the secrets of our solar system's largest planet.